Shall we start? Everything is fine? It's clear?
Yes, Dr. Talebi, the floor is yours. Please start.
Hello, Professor
Okay,
Talebi.
yeah.
Good evening.
Hello. Yeah, good afternoon, everybody. Yeah, let me start then. Yes. Good afternoon, everybody. Yeah, shall we start?
Yes, please.
Okay. Good afternoon, everybody. Welcome to the workshop on cyber physical system security, a controlled theoretic approach, which is done by myself, Dr. Talebi, and my associates, Dr. Iman Sharifi, and Miss Firuzman and Miss Behnian. So like I said, the workshop is on cyber physical system security. And I'll be with you about a couple of minutes to introduce the topic, and then my colleagues will do the rest. So as an introduction, in this workshop, what will we cover is that what is the cyber physical system? Any system which is the integrated from information, communication, and computation interacting with the physically engineered system is called cyber physical system. So the existence of cyber will allow the intruder, the adversaries, to penetrate to the network of the system and might create lots of problems. So what would be the cyber security? Cyber security is practice of defending this cyber physical system, the network and the data from the malicious attack. But we have to know and we have to remember, and the basis of our work from the control engineering point of view, that we assume that there's no computer engineering algorithm that can ban the intruder from getting into your network and into your system. Once they penetrate the system, they know everything about the system. So what algorithm from the control engineering point of view we shall develop to defend this system, knowing that the network as a whole and the adversaries can penetrate to the network. So what is the definition of the cyber attack? So if this transmitted data loses either the confidentiality, the accessibility, or integrity, you say that the system is under attack, and you know many cyber attack which is growing in the past couple of years. So what would be the challenges once we are dealing with the cyber physical system? First of all, we know that the intruder and the adversaries and the attacker are one step ahead of the defender, because they are working on the new types of attacks that we are not aware of the attacks. Like I said, we have to categorize different type of attacks which is existing right now. The zero dynamics attack, the repeated attack, and this and that. But the attacker is working to develop new attacks that the defender is not aware of that. So the first thing is that we have to categorize all types of cyber attacks. The second thing is that we have to detect this attack on time before it is damaged to the country's infrastructure and to the system. So it's very important. The timing is very important here. If it's predicted and detected on time, you can develop the algorithm which you have to think ahead of time what algorithm you need to develop to either prevent or recover the system from the attack. And this is a very challenging and difficult task, especially if you knowing that you don't know that what type of attack the adversaries are working right now. So the other thing is the recovery of the system. Once you detect the system, suppose that there are many algorithms that are working on preventing the system from attack, but there is a chance that these algorithms are not successful. So the intruder attack the system. So the next step is that once the attack is happening, then you have to predict it, and then you recover the system from the attack. So you have to work on an algorithm on the recovery algorithm and scheme. So we know that although that I talk about the infrastructure, in the infrastructure, the computational power is very, huge. But the attack is happening everywhere, into your car, into your robot. Once you have a network, there is a chance of getting under the attack. So in those applications, there are not much computational power. So either the prevention or detection or recovery algorithm might have light computation. So, like I said, you need to develop defense strategies for stealthy attack and for the attack that is not known a priori. It means that not categorizing means that it didn't happen previously. So these are the topics that my colleagues will presenting to you, and I hope that you enjoyed the talk. Dr. Sharifi and Ms. Firuzman, Ms. Benya, I am done, and I'm listening to your presentation.
Thank you very much. Please wait. Hello, everyone. Do you hear me? Okay. Hello, everyone. I thank Dr. Talebi for good explanation he provided. Thank you for joining us at workshop, which is cybersecurity in cyber-physical systems, as part of International Conference on Robotics and Mechatronics, ICRoM 2021. My name is Iman Sharifi, Assistant Professor in Electrical Engineering at Amir Kabir University. In collaboration with workshop organizer, dear Professor Haidar Ali Talebi, the head of Electrical Engineering Department, and Dr. Mehran Dibaji, research affiliate of cybersecurity at MIT Sloan and Department of Mechanical Engineering at MIT. He's joining us from Boston in Massachusetts. It is first morning there. Thank you very much. And also Dr. Hamid Reza Baghai as the Associate Research Professor of Electrical Engineering at Amir Kabir University of Technology. Moreover, our very dear colleagues Elnaz Firuzmand and Kosar Behnia, the PhD students of our laboratory. We would like to welcome you to Cybersecurity Workshop. I do not have much time, and I have to finish my presentation in 30 minutes. So first of all, before we get started, I would like to draw your attention to a few points. The workshop is being recorded and broadcasted on my personal website, YouTube, Aparat, and maybe ICRoM website. Full workshop information, including the speaker's name and details about the talk, can be found on the workshop webpage. You can scan the following QR code for more information, or going into the showing link b2n.ir/ICRoM_W4. We encourage interactive communication. Please comment and ask questions through the chat box at any time. If you had any question, feel free to type your question and we will go over your question. So on behalf of the workshop organizer, I would like to sincerely thank the invited speakers, which made it possible for us to organize this unique event. Thank you so much. The workshop is composed of 5 talks, including the Dr. Talebi's talk. And after that, my talk is about Industry 5.0 and our new established laboratory. My dear friend, Dr. Mehran Dibaji will talk about resilient control approaches. My dear colleagues, Elnaz and Kosar will talk about attack classification and detection. Lastly, my dear colleague, Dr. Hamid Reza Baghai will talk about resiliency in power electronics systems. Mission statement. In this workshop, we collect expert opinions from researchers who are actively contributing to the field of cybersecurity. This workshop seeks to present recent efforts related to cyber physical models and advancing Industry 5.0 technologies. The goal is to bringing diverse researchers from both control and cybersecurity and explore how to maximize the progress in the multidisciplinary field. In addition to inform and further accelerate research in both control and cybersecurity fields. We sincerely hope that this workshop creates an interactive and interdisciplinary dialogue between leading researchers, young researchers, and industrial sector focusing on cyber physical systems, bringing new perspectives in the synergy between resilient control and cybersecurity. Okay. The content of this slide will be as follows. First, the overview and introduction of the content will be presented. Then we will deal with the development that have taken place in the industry from the first generation to the fifth generation. After this, we will examine the role of control theory in the fifth generation of the industry. Then we examine the recent cyber attacks that have taken place in Iran and have become a problem for Iran. After that, necessary and sufficient condition for construction of the fifth generation industry laboratory. And after that, our goal for the construction of this laboratory will be explained. Okay. Sorry, please turn off your microphone. Somebody is talking. Okay. At the end, some recent projects that have been done by our students in this laboratory will be introduced. First of all, I would like to introduce you to the topic of IoT and cyber physical systems, the ability to have a unique address for the various objects we deal with on a daily basis, and the unique ability to access each of those objects can be provided by a collection called Internet of Things. Another features that the Internet of Things can provide us is the connection of all devices on the network to each other, which means that in addition to this device can provide information to human and be monitored by humans, there is the ability that these components and the device talk to each other. Also assume that a person is not at home at certain times of the day. So system utilizing the data from the previous days can intelligently decide at what time the heating and cooling system will be turned off or on based on the time the person returns home. For this person, the cost of electricity will be lower, and also the amount of pressure that is applied to the electricity network and the savings that are actually made will be to benefit all the consumers. In public transportation system, I mean smart transportation, city street traffic is managed by the Internet of Things. The city management system is aware of amount of traffic on different streets, and according to that, it schedules the traffic lights in order to impose the minimum traffic on the city. On the other hand, autonomous cars can be noticed to information of the city management and choose the best route to move to reach the destination faster and to impose less traffic on the city. IoT-based medical systems, I mean smart health, can also remotely report the patient's condition to the central system. Okay, there will be time for question at the end of the workshop. Okay. In a critical situation for patient, automatically send alerts to those around them and inform the nearest clinic to the emergency department to present there over the patient. On the other hand, concepts such as preventative maintenance and predictive maintenance are widely used in the field of IoT. For example, hospital equipment should be referred to the maintenance unit for review after a while, and with the preventative maintenance system, we will find out when it's time to replace and repair a device. Also, the municipal electricity management network, which includes producers and consumers of electricity, can interact with each other on the Internet of Things based on the consumption of each grid. Moreover, different energy sources are synchronized with each other to have the best adaptation in the form of voltage and frequency. Such a system is called the smart grid. My dear colleague, Dr. Baghai, will explain more about these concepts. Another example is remote robotics that has many uses in medicine and industry. One of its applications in medical science is telesurgery, and the other application is telerehabilitation. The platform when the robot and surgeon console communicate with each other is the IoT platform. Today, with the use of 5th generation of telecommunication network, I mean 5G, the amount of latency is greatly reduced, and the information of the force and the position of the patient and the doctor for teleoperation is well transmitted. Okay. The topic of telerobotics is a detailed topic that is in the past months, a workshop was presented by this team and will be discussed in future workshops soon. The next issue is platooning of cars and their motion in a regular line or in a specific geometric form. This will result in many profits, including higher speeds and discipline on highways. These vehicles can also communicate with central unit, be aware of the amount of traffic, and travel shorter roads to reach the destination. Now, the same concept can be applied to industry, which means that we have a large number of devices in factories, in cities, and in larger scale systems, including sensors and actuators. Now, with a cyber system from the above part of the hierarchy, all these devices are connected to each other and can talk to each other. At the same time, the human, as the important element in giving high-level orders, can play a major role in the control loop. In the next slide, it will be stated that the cyber physical system in the interaction with each other need a very strong network, a very strong processing platform, as Dr. Talebi mentioned, which together is interpreted as the 5th generation industry. In this slide, different layer of IoT can be seen. The measurement layer, including sensors and actuators and portable devices. Network layer with blue line, which includes the type of communication protocol and how the hardwares are connected to other devices and the network. Also, the middle layer that includes API, databases, and network security with orange color. On the other hand, the application layer where the software interacts with human, and the next layer is business layer, in which machine learning, optimization, and deep learning are used to grow the business with the brown color. The cyber physical system introduced in the previous slide consists of a triangle, including control, calculation, and communication. Each physical process containing sensor and actuators in the network platform can connect to control or software system called cyber system. And in any part of this communication, malware and malicious behavior can sabotage, as Dr. Talebi at the starting of this workshop presented. So the concept of cybersecurity is introduced. Here, if we want to tell you the history of industrial developments from the 1st to 5th generation, I must say that in the years between 1780 to 1870, the first generation of industry was being formed due to mechanization and steam machines. The second generation of industry was formed from 1870 to 1970 with the invention of electricity. In this industry, mass production was formed using assembly lines. The third generation of industry was created in 1970s using electronics and computers and automation. Based on them, the third and half generation industry was started in the 1980s. In this era, we reached the globalization by offshoring of products to low-cost economies. Today, we are in the fourth generation industry, which is actually used to automate projects by utilizing artificial intelligence and data analysis tools. However, in the fifth industrial revolution, or the Industry 5.0, the focus is on the interaction between man and machine. Which means that the human intelligence operates in harmony with computer cognitive science. As mentioned in the figure, by involving human back in industry production and interacting with robots, workers are able to perform value-added activities that led to mass customization and personalization for customers. This revolution is about the interaction and participation of artificial intelligence and human intelligence. The revolution will be about understanding and not being afraid of unique feature of artificial intelligence, such as non-bias, accuracy, and data, so that employers can make more accurate and better decisions for their organization. Okay, as you can see in this slide, Industry 5.0 is based on three slogans: human centricity, sustainability, and resiliency. Industry 5.0 is a model of next level of industrialization characterized by return of manpower to factories, distributed production, intelligent supply chain, and hyper customization, all aim to deliver a tailored customer service time after time. So talking about human centricity, the human centricity solution and human-machine interaction technology interconnect and combine the strengths of human and machine together. Sustainability is about using renewable energy and managing grids. My dear colleague, Dr. Baghai will talk about this fact more truly. Increase in industrial production normally requires more energy and increased carbon emissions. Innovation in Industry 5.0 can reverse this trend by a smarter production planning and the use of more energy-efficient technologies. Resiliency means that the system is robust and resilient against cyber attacks. Resiliency means that if an attack is acting on your system can identify and reject it, so it can come back resiliently to its previous manner. In this slide, technology enablers will be discussed in line with the fifth generation industry. Some of the most important technology enablers are as follows. An industrial blockchain that provides us with the ability to communicate between all devices or between in situation invisible from above part of hierarchy or governments or be hacked by others is called the blockchain. The next technology is UAVs, which provide user with the ability to transport, inspect, coverage, and imaging. The next technology is exoskeleton robots, which have many applications in industry, military, and medicine. For example, a factory worker can move heavy equipment by wearing an exoskeleton robot without incurring the slightest pressure, and the weight of the load is borne by the robot. Also, in a medical field, it helps patients who have difficulty walking to perform rehabilitation operation to walk better. In addition, it helps patients with paralyzed legs to be able to walk. The next technology is the add-on technology or 3D printing, which allow any equipment that has a 3D model to be printed in high quality and 3D. This equipment can be in an industrial equipment, or it can be an organ of the human body, such as a tooth, or a part of a skull that is carefully printed and replace the lost one and defective parts in the body. The next technology that is groundbreaking is in the field of the fifth generation of telecommunication. For example, by relying on fifth generation, the speed of information exchange between these devices and the delay between them can be greatly optimized, and the round trip time, RTT, between communication system and telemedicine devices can be done with minimal delays. The next technology is mixed reality, where the user can imagine themselves in environment other than where they are standing. For example, a doctor can imagine himself on top of a patient undergoing a surgery, or a house buyer can imagine himself inside that house. These were some of the most important technology enablers that enables Industry 5.0. In this section, we will explain the role of control theory in the fifth generation industry. First, we will explain the courses taught in the Faculty of Electrical Engineering in American University related to the Internet of Things and Industry 5.0. The graduate courses are as follows. You can see Industrial Internet of Things that is taught by me, Advanced Instrumentation and Fault Detection and Fault Tolerance Control System that is taught with Dr. Talebi. And the other courses are undergraduate courses, and they are as follows: in Introduction to Instrumentation, Industrial Control, and Digital Control. In this slide, the challenges in Industry 5.0 that can be explored and addressed by control engineering are outlined. The first one is resiliency control in communication problems. For example, uncertain communication channels, delay, jitter in communication channels, bandwidth limitation. The second one is the resiliency to various cyber attacks. My colleague Elnaz and Kosar will discuss about them, including zero dynamic attack, replay attack, denial of service attack, COVID attack, false data injection attack, and bias injection attack. The third one is telerobotics, including surgery and laparoscopic robotics, telerehabilitations, and much more. The fourth one is battery control and management systems. The fifth is maintenance and monitoring of health or military equipment I mentioned in previous slides, including predictive maintenance and preventative maintenance. The sixth is smart microgrids. Dr. Baghaei will talk about it truly. Control of drone missions is the seventh one. And control of autonomous connected vehicles, including platooning, swarming, formation, and consensus. In this slide, I will talk about recent cyber attacks in Iran. In this slide, I will briefly talk about well-known cyber attacks occurred in Iran recently. Iranian officials have confirmed that all 4,300 fuel and gas stations in the country had been shut down following a cyber attack. About 3 or 4 days after the cyber attack, most of these centers were still unavailable and refueling was done manually or offline. The next recent cyber attack was about a cyber group which hacked the CCTV cameras of Evin prison. During this operation, the prison cameras were completely hacked, and their images were recorded for a long time and made available to all people. Supervisory room monitors also showed image other than the cameras as well as showing vague text to confuse the managers. The next cyber attack occurred on 2020, in which R1 cloud computing infrastructure in the data center faced cyber attack aimed at destroying and deleting customers' information. The attack affected about 16% of R1 cloud's customers. As a result, with the spread of the attack on the evening of March 17th of 2020 and the damage to customers' data in these data centers, all accesses were cut off in order to prevent the progress of damage. The next important cyber attack was the attack on Natanz equipment. Experts' assessment showed that the cyber attack has caused power outage in all parts of this facility. The next attack was the Stuxnet, which damaged to the nuclear program of Iran. Stuxnet is a malicious computer worm first uncovered in 2010. Stuxnet targets supervisory control and data acquisition room called SCADA and is believed to be responsible for causing substantial damage to the nuclear program of Iran. As can be seen, the OSI model has 7 layers that cyber attacks can enter any of these layers from the physical layer to application layer. But suppose antivirus and firewall do not have the ability to counter a cyber attack, a virus or malicious program enter into the system, and the attack survives by going through these 7 layers. In this case, the detection algorithm embedded outside of the OSI layer, control layer of the sensor and the actuators are tasked with the detecting and treating the attackers. Such algorithms are very similar to the control algorithm used between the 1990s and 2010s for fault detection and tolerance in control systems. But the big difference that will be expressed in the next slide is in the intelligence of the attacker compared to the fault that occur in the system unintentionally. This is the key. In this section, the difference between fault and cyber attack will be discussed. The fault is caused by an unwanted event within the system and is unintentional. For example, a car may have a flat tire while driving, or airplane's engine may catch fire while flying. Other control system and actuators must now operate in such a way that they will arrive the final destination with minimal damage to other part of the vehicle or aircraft. However, in the cyber attack, the attacker is completely deliberate and intentionally sabotaging, and therefore the system is exposed to a deliberate damage from an external source. Therefore, detecting and treating cyber attack requires more up-to-date and intelligent controllers in compared to classical controllers. In this regard, as the last slide that I have prepared for my presentation, I would like to mention that we have established a research laboratory called Control in Industry 5.0 at Amir Kabir University of Technology, which is based on the control objectives mentioned in the previous slides. Investigating control challenges from 5th industry in the field of cybersecurity, creating an environment for skill development and introducing students to the role of control theory in the Industry 5.0, creating an environment for implementing control algorithm to improve Industry 5.0, creating an environment for introducing expert engineers and scientists to the role of control theory in the fifth industry are the aim that we have constructed this laboratory. Several research projects by graduate and undergraduate researchers have been done in our research laboratory based on the IoT and Industry 4.0 or 5.0 during last 2 years. As a short list of them, you can see control of intelligent network of water and sewage distribution based on the Internet of Things, platoon control of the transportation of heavy-duty vehicles based on the Internet of Things, implementing IoT-based path planning and platooning control of autonomous vehicles, implementing and formation control of playmaker and supported robots in soccer league in the context of Internet of Things, and much more were the recent projects that have been done in our research laboratory. Well, this is where my slides end. Excuse me if I explain a little quickly due to lack of time. I hope you find the content useful. Here I hand over the podium to our two good research assistants, Ms. Behnia and Ms. Firuzman, and I want them to continue the discussion. Thank you very much. Temporary goodbye. Ms. Firuzman and Ms. Behnia, the floor is yours. I will answer your questions in the chat box. Thank you very much.
Well, thank you, Dr. Sharifi, and thank you, Dr. Talebi, for your valuable presentation. So now let me share my screen. So do you have my slides? Please confirm by voice because I don't have.
Yes, we have your slides and your camera.
Okay, I can start then. So again, thank you, Dr. Sharifi, for your talk. And then I will continue to the next part of the workshop, which is the joint presentation on introduction to cyber attacks in cyber physical systems and overview of detection and defensive strategies, given by me, Elnas Firuzman, with Ms. Behnia. We are both PhD students from Department of Electrical Engineering in American University of Technology. So before I begin, I want to give an overview of the materials that we are going to discuss in this lecture, which is divided into two parts. In the first part, we will discuss on a little bit of introduction to the security of cyber physical systems, and then we discuss on different types of attacks, the way that we classify them, and then various types of cyber attacks in cyber security of cyber physical systems are presented. And in the next part, my friend will discuss about detection strategies in cyber physical systems, ended by defense algorithms that are most common in cyber physical systems. So as an introduction, I want to start with a question, with a basic question, why we care about security of cyber physical systems. So cyber physical systems is resulted from the interaction of physical systems and the cyber domain. And what I mean is the integration of a physically engineered system with the information, communication, and computation. So we can see a rapid change of, for example, a radical shift, from the closed wired physical systems to the wireless and open network that are vulnerable to cyber attacks. So any invader can infiltrate to this cyberspace and change the information that are transmitted through the communication links between the sensor and actuators or any other elements in the cyber physical system. So as the information is one of the most important things in controlling the network control systems, we should be aware of security breaches that are often considered in this literature. One of them is confidentiality breach, which is the unauthorized information release. As you might guess, for example, an attacker just monitor the data that is carried out in the communication link, or the integrity breach in which an attacker just corrupt the sensor data. For example, in the feedback control systems, have an unauthorized information modification. And another security breach that should be considered is availability, in which we have the unauthorized denial of use of information. For example, an attacker just block the way of transferring the information, the communication links between the sensor and actuator nodes and the computational control units. So based on these definitions, so there are some important topics to consider hereafter. So we should be aware of different types of cyber attacks. With this kind of knowledge in our mind, then we can be equipped with the knowledge to efficiently design detectors for detecting attacks, and then we can use that for designing resilient control strategies against cyber attacks. To define different types of cyber attacks, we can refer to one of the most important categories, which is the DDD category, that I included it from the paper of Mr. Dibaji, that is one of our presenters. Based on DDD category, attacks can be categorized into three parts. One of them is disclosure, deception, and another is disruption attacks. Disclosure attacks refers to any intrusion that includes eavesdropping. For example, as you could see in the diagram, an attacker can just infiltrate to the cyber layer between the sensor and the computational control network, and then listen to the data that is transferred over this network, or it could be as an infiltration in the communication link between the actuator nodes and the control unit, and monitor the data from that. And then it could easily apply some machine learning algorithm to get some knowledge about the system and the control strategies that are used in here. Another thing is deception attacks, which corresponds to the corruptions of the signals. For example, if you could see false data injection attacks in the literature. In these types of attacks, the attacker just modify the data. For example, it can modify the sensor data that is measured from the output of the system, or it can modify the control commands that are made from the control units. So another type of attack, as we discussed, is disruption attack, which corresponds to another active intrusions where the signal may either be blocked or delayed. Delay the information. For example, in the same situation that attacker just infiltrate to the cyber layer, it can occupy that communication link for a while and then block that way and don't permit the data to transfer to its destination. So with this in mind, if we see closer, we can see a direct mapping between the security goals that we aim while designing a secure cyber physical systems and the attack models that we discussed earlier. So you can see that disclosure attacks, when disclosure attacks actually launch on cyber physical systems, so the confidentiality of the cyber physical system is targeted, and when the deception attack is launched on the system, so the integrity of the cyber physical system is not ensured, and in disruption attack, the attacker just prevent the information to reach its destination. The cyber physical system lacks availability. So now we want to take an overview of different attack classification. One of them is based on active and passive attacks. In passive attacks, attackers does not change the transmitted messages. I mean, it just eavesdrop the communication links. And for example, in denial of service attacks that we will discuss in the later slides. And we have active attacks, which corresponds to, for example, types of attacks that the attacker change the data in such a way that remains stealthy while damaging to the system, makes damage to the system. For example, we can name zero dynamic attack, replay attack, and COVID attack that we will discuss in much more detail in the later slides. Another attack classification methods that is very common and famous among the scientists in control theory is based on the available resources. Let's assume that an attacker wants to design an attack. So it might need 3 kinds of information or resources to design an attack. For example, it could be the model knowledge of the system, I mean the state matrix or the input matrix or output matrix of the system, or it could be the accessibility to disclosure and disruption resources that makes up the 3-dimensional cube that you can see in this slide. Let's, for example, name one of them. For example, the Kavita attack is one of the most strongest attacks that have all access of the resources that are needed for designing an attack. It has the full knowledge of the model, while it has the while it has the full information and access to the disclosure resources, so it can eavesdrop and record the data from the input and output of the system, and then it has the full access to disruption resources, so it can modify the data in the input or output to remain stealthy. And another example is, for example, eavesdropping attack. As you could see in this picture in here, it just needs in the line of the disclosure resource axis, so it just needs to have access on disclosure resources, and there's no need for a model of the system or disruption resources. It just records the data, and it's in a passive tense, and then it might use some machine learning algorithm to just obtain information about other things, for example, the knowledge of the model. So let's explain more about these types of attacks that we have seen in this slide or the earlier slides. One of them is Kavita attack, and we want to talk about the strategy. In the Kavita attack, the attacker listens to the transmitted data, I mean the input and output data of the system, and then estimates the system output to the transmitted input data, whether it could be by the exact model of the system or it can be obtained by the passive phase, for example, using such kind of machine learning algorithm, and just obtain the model of the system. And then it adds disruptive signals to the system, and then change the output data to the estimated normal data to hide the effects of the injected malicious information. As you can see, this is the most strongest type of attack. And if we want to summarize its properties, we could see that in the sense of the having access to different kinds of resources for launching an attack, it has the access to have access on exact model of the system, and at least 2 communication links needed to be hacked. For example, the output for replacing and the input for changing the data. And attack cannot be detected by monitoring output signals by any conventional observers that are common in the field of control theory or fault and control systems. Another type of attack is DOS attack, which is the abbreviation for denial of service attacks. Based on its strategy, the attacker adds numerous data, a lot of data, to the router queue, and then the router queue becomes full and no other data can enter in this phase. For example, the router queue becomes full in the feedback control system for the router that sends the information from the sensor to the control systems, or from the control system to the actuator. So we have either the data could be either delaying or actually just preventing to reach to its destination. So in this part, in some literature, in some papers, we can see that the scientists model it as a injected delay in the system that can destabilize the system. If we want to say that what is the DOS attack property, it is obvious that there is no knowledge regarding the system's dynamic. So another type of attack is replay attack that is according to a strategy, it consists of two phases. First phase and the second phase. The first phase is a passive phase, when the attacker just eavesdrops or listens to the transmitted data from the communication links in the specified time, for example, from the systems running to a specified time, for example, T seconds. And then in the active phase, the attacker replaces the sensor data for the following T seconds from that, starting from the previous T seconds, and then with the lesson data, and then the attacker adds disruptive signals to the input signals. So you could see the attacker adds disruptive signals, malicious inputs to the input of the plant or the cyber physical system, but in the output, we just observe the previously recorded data, for example, from time 0 to T seconds. As you could see, in replay attacks, there is no need for the knowledge of the system. There's no need for the model of the system, and the attacker just needs to hijack two communication links, the input data for disturbing the control commands and the outputs link to just broadcast the latest recorded signals. The final type of attack is zero dynamic attack. This is the most related attack to control theory. Based on its strategy, the attacker adds a signal in a zero direction of the system, and so it cannot be detected by monitoring the output signals. So while the external dynamic of the system continues to the normal mode, the internal dynamics of the system may be destabilized and the states goes to infinity. So if we want to summarize the attack properties in this kind of attack, it needs information regarding an exact zero direction of the system to give input in that direction. And we only need one link to be hacked in order to perform the attack. So this is the properties of the zero dynamic attack. So this ends up my talk, so I can invite my friends, dear Kosar, to continue discussing about detection and defense mechanism in cyber physical systems. Thank you.
Well, can you see, do you have my voice and my slides?
Yes, you have.
Okay.
Let's share.
What?
Go to a slide share.
Yeah, I went. Okay, thank you, Miss Firuzman. Well, I'm Kosar Behnia, and I'm gonna continue this workshop. Well, various cyber attacks has incurred lots of human and financial losses to the countries. A Stuxnet attack, for example, as mentioned, damaged lots of Iranians' nuclear equipment. In order to prevent or even minimize the effect of this attack, researchers have come up with different strategies and ideas to detect different cyber attacks. In this section, we're going to have a quick overview on these various strategies. Well, a long time ago, in order to detect cyber attacks, researchers suggest using some cryptographic strategies. Cryptography is the science of analyzing and constructing protocols that to prevent third parties or public from reading a private message. Modern cryptography started by using the concept of public key. And the goal and the main idea of this field is to make sure that the data transmitted between sender and receiver cannot be revealed via an unauthorized access. Yes.
Do you hear me?
Yes.
We don't have your slides. I think you should go to a slideshow and enable it. Okay?
Okay.
I do have the slides, actually.
You have it?
Screen mode. Maybe you want to go.
Let me export it to PDF.
Or you can click on the full screen on the right bottom side of your slides. Maybe that
Oh,
makes
my friend is there. Okay, I converted to PDF.
what this is nice.
Do you have my slide right now? Can you see them?
I see your slides.
Okay, should I continue?
Are you in the slide number 18?
No, I'm switching.
No.
Yeah,
We
now
are
I'm
not seeing
I'm
your
on
screen. The
slide.
screen you are presenting is different from what we are seeing.
Okay, let me check it.
Maybe you can stop presenting, sharing your
Yeah,
desk.
yeah.
Yes,
I'm
do it.
stopping it. Let me just convert it here. Okay.
Okay, we have now your PDF.
Yeah, okay, I just keep in screen mode. Can you see it right now?
Yes.
Okay. Okay, so I start. As I say, various cyber attacks has
We
incurred
are
lots
seeing
of...
the slide number 17. Are you here?
Yes, I'm exactly right here. Various cyber attacks has incurred lots of human and financial losses to the countries. A Stuxnet attack, for example, as mentioned, damaged lots of Iranians' nuclear equipment. In order to prevent or detect these cyber attacks, researchers have come up with different strategies to detect various cyber attacks. In this section, we're going to have a quick review on these strategies. Well, a long time ago, in order to detect cyber attacks, researchers proposed using some cryptographic strategies. Cryptography is the science of constructing and analyzing protocols to prevent third parties or public from reading a private message. Modern cryptography started by using the concept of public key. The goal and main idea in this field is to make sure that the data transmitted between sender and receiver cannot be revealed by an unauthorized access. In this field, authentication can be checked by sending a secure message between sender and receiver, and encryption and decryption strategies can be used to maintain confidentiality of the data. Different methods can be used for encrypting messages, such as symmetric or asymmetric cryptography. However, if attacker somehow can eavesdrop the transmitted data between A and encryptor or B and decryptor, he will be able to listen the whole transmitted data. A and B can be any of the plant, sensor, or actuator in CPS structure. Therefore, cryptographic strategy, although very useful, are not enough, and we need some control-arised strategy to detect different cyber attacks. Well, let's start by zero dynamic attack detection strategy based on control theory. One way to detect zero dynamic attack is by changing plant's dynamic, I mean A, B, C, or even D. The change should be in a way that the new structure doesn't share any similar zero dynamics with the previous one. Since the zero dynamic attack signal is in the direction of the zero dynamics of the system, if attack occurs, considering that the new modified structure doesn't have any common zero dynamics with the previous one, the attack can be detected by monitoring the output signal. Unfortunately, changing the planned structure in this predefined way is not always practical and possible. Therefore, we need other methods to detect this type of attack. We know that if attacker wants to perform zero dynamic attack and remain stealthy at the same time, he needs to have somehow an exact model of the zero dynamic of the system. This exact model is usually obtained by listening to the input-output data transferred over the communication link. If attacker somehow can't obtain an accurate model of the plant by listening to these transmitted data, he won't be able to perform zero dynamic attack and stay stealthy at the same time. One way to achieve this goal is by designing numerous controllers and switching between them. Switching between different controllers make it hard for the attacker to find an accurate model of the plant and perform zero dynamic attack. Therefore, this strategy can greatly prevent zero dynamic attack, although it needs to design affluent number of controllers. There are other methods to detect zero dynamic attack in sample data system. For example, by designing a multi-rate adaptive controller and choosing appropriate sample time, such that the zero dynamics of this closed loop system become stable. After that, considering that the zero dynamic attack signal is in the direction of the zero dynamics of the system, the attack signal converges to zero over time. There are other methods to detect this type of attack, for example, zero placement strategy for discrete system, and methods which are based on the difference between initial condition of the system and those chosen by the attacker. Well, let's move on to replay attack detection strategies. There are lots of ways to detect replay attack. One way is by adding a specific field to the header of the transmitted data. The added field should have some main feature. First of all, it should be time variable, meaning that if attacker wants to attack system by simply copying the past data through the communication link, we will be able to detect it simply by checking the header of the data. Since it is time variable, we can easily distinguish between passing data and the past one. Second of all, the added field should be random in nature. This randomness prevents attacker to predict this added field by listening to the transmitted data and perform some modified version of replay attack. Another important feature of this field is that it should be verifiable on both controller and system side. Being verifiable on both controller and system side means that if attack occurs, both controller and system side will be able to detect it and perform some necessary step to minimize its effect. Unfortunately, generating a true random signal which cannot be detected by listening to the transmitted data and at the same time be verifiable on both controller and system side is a challenging task. And despite scientists' non-stop effort, till now they can only generate an approximation of this ideally random signal. Therefore, researchers propose other methods to detect replay attack. Another famous strategy for detecting replay attack is watermarking algorithms. In this algorithm, first a length of a time window is chosen. After that, at the end of each time window, the input of the system is changed slightly, for example, by adding some noise or perturbation to the input signal. At the same time, we try to predict the output of the system by some structure, for example, some observer. If the system is under replay attack, the effect of this change, I mean the change in the input signal, cannot be seen by monitoring the output signal. Therefore, the difference between the observer output and the output data of the system will be bigger than a threshold, and the attack can be detected. In covert attack, like zero dynamic attack, in order to remain stealthy, attacker needs to have an exact model of the plant, which is usually obtained by listening to the input-output data transferred over the communication link. Another way to prevent attacker from obtaining this accurate model and performing covert attack is by inserting random matrices on plant and controller side. Random matrices makes it hard for attacker to obtain accurate model of the plant. There are infinite choices for these random matrices, but ideally they should be chosen in a way that their effects on the steady state behavior of the plant is minimized. Resilient algorithms, which are arise from control theory, can also be very useful in detecting different cyber attacks. The goal of these algorithms is to make sure that the system can follow its desired behavior despite being attacked. Famous algorithms of this category are WMSR and reputation-based algorithms. WMSR is an algorithm which is usually used for multi-agent system. A remarkable advantage of this algorithm is that it is only based on local data, meaning that agent doesn't need to have any global information regarding graph communication topology to implement this strategy. In this strategy, it is assumed that maximum number of attack agents around each agent I is known. If we assume at most if attack agents are around each agent I, the algorithm can be summarized as follows. First, every agent sorts its incoming data from smallest to largest. Then every normal agent remove F largest and F smallest of its data received from its neighborhood. And finally, agents compute the control signal using the remaining data. It can be proved that if some system use WMSR algorithm, it can continue its desired behavior despite being attacked if the graph topology if the graph communication topology is at least 2F+1 robust. Another famous efficient algorithm of this category are reputation algorithms. They are applicable for multi-agent system, both leader-follower and leaderless structure. These algorithms are composed of two main parts: first, detection and mitigation. In detection, our goal is to try to detect attack, and in the mitigation phase, our goal is to reduce the effects of attack on the control signal. In detection phase, the attack can be detected by using some trust metric. There are lots of ways to generate this trust metric, but one way is that each agent I evaluate the difference between its incoming data from its neighbor agent J and its expected value. If this difference is less than a threshold, we can increase our trust towards agent J, and if this difference is bigger than a threshold, we can decrease our trust towards agent J. In mitigation phase, considering that in multi-agent system, the control action is usually obtained by some weighted structure of the incoming data, it is enough to reduce the weights of the less trusted agents to mitigate the effects of the attack. Artificial intelligence and machine learning algorithms have been very useful in solving some of our most perplexing and sophisticated problems. Therefore, we somehow expect them to solve some of our cybersecurity problems too. Different AI-based structures such as GAN, SVM, and online common can be used to train an anomaly detector to distinguish between normal and attacked data. Of course, this AI structure needs a huge training set in order to be trained. And therefore, this approach can be useful only for attacks that this huge data set can be obtained for. Game theoretic approaches have been also very useful in finding some defense strategy. In this field, the attack is usually modeled as a zero-sum game, and the design and the defense strategy are designed by considering the possible set of actions that attacker can take. That's end up my part. I hope it widen your horizon in cybersecurity defense and strategy, and it encourages you to actually work in this field. To have a quick conclusion, in this part, we saw different types of cyber attacks, and we saw different classification for these attacks. We conclude that cyber attacks have many destructive effects on cyber physical system. And we saw that cryptographic strategy are not enough for securing cyber physical system. And finally, we saw some control arise security strategies that can help us to maintain security of cyber physical system. Thanks for your attention and your time. Now I invite Dr. Dibaji to continue this workshop.
Oh, thanks a lot for great workshop and inviting me. It's a great pleasure to talk for this workshop. Okay, thanks. The talks were actually great. I learned from some of them, and I hope this one is also helpful for you. Please feel free to ask any questions if I have to jump after the talk because it's actually working day for us. It's now 8 a.m. in the morning. I'm skipping some of the meetings now, but feel free to reach me through email dibaj@mit.edu, or we may have some time after my talk, maybe 5 minutes, if you have questions. So I guess Mr. Sharifi introduced generously, but I'm going to add some of my previous industrial experience. I was in a company called Aeroflight Sciences, which is a Boeing company, and now it's part of Boeing Research and Technology. We were working on cybersecurity of autonomous air vehicles for a couple of years, and currently I'm working in a power system company called Fluence Energy, which is an energy storage company, mostly on control side. I'm ICRoM senior member and associate editor of ICRoM Control Systems Society. Before that, I was in MIT doing postdoc. Still, I'm in MIT cybersecurity at MIT Sloan as a research affiliate, doing some mentorship and advice to the research in this area. So I think previous presenters talked very well about defense mechanisms, but just to make sure that at least things are consistent with my presentation, I'm interested in giving another perspective, which is coming from this review paper, which I encourage you, if you haven't seen it, please take a look, because it's getting a lot of attention from the time we published this, and it's becoming a part of a Springer book chapter soon in I hope by end of 2021, but it's, I think, under publication. So attacks occur and they have an impact on the system. From the time they occur, if you postpone the occurrence of the attack, you are preventing the attack. Cryptography algorithms, randomization, anything that is just making the work of attacker harder and harder is prevention. What I'm talking today is more on the resilience side, which you don't care when attack has happened. You don't care why it has happened. You don't, and you are not trying to detect who is the attacker. Maybe what is it doing? Like you don't care about those. You are just minimizing its impact. And why do you care about resilience? Because as mentioned by Mr. Sharifi and I believe maybe Ms. Gehnia, so detection of the attack is not easy, or is not at least as easy as we think or we see in fault detection algorithms. So we need other types of algorithms that is just minimizing its impact while it's happening. And there is recovery and detection that you are just stopping the attack. When you detect, what you do is just isolate the type of the part that is attacked. And with that, you are recovering the system from the attack. That's why I usually put detection and recovery in one section as a defense mechanism. Okay, with all of these, and you need probably all of them, you may need one of them, depending on the system, depending on your problem, but a very comprehensive defense mechanism includes all. Sometimes people call prevention and resilience security, and the other part resiliency. That's another way of looking at it, but I don't like it because I think when we say resilience here, we should call this resilience. But people do it because they don't want to add prevention, which is like an active way of looking at the problem before anything happens to be part of resiliency. And I think that, like in the presentation of Dr. Sharifi, when he was talking about resiliency, he's not probably talking about preventive algorithms here, just as a guess. So I have some previous works from 2014, 2012 when I started my PhD in Japan, but I brought those relevant ones. One of them was the review paper I talked just now. The other one, we added some works in privacy, which is on the confidentiality side of the attacks, and these are going to be published as a book chapter soon. I have a bunch of papers in MSR algorithms. All of them are in resilience, and previous presenter just talked very well about it. But we also applied MSR algorithms in autonomous vehicles, in coordinated movements. We have one paper on detection and prevention on power systems, wide area control systems, that I believe Mr. Baghai is going to talk about. Not this one, but his own research, but in the topic of wide area control systems. And the one that I'm presenting today is actually a new work that we published actually 2 years ago, but it's being published as a journal paper soon in European Journal of Control. And this work is with Mr. Safi. He's in Iran. So let me just go back and maybe look at the problem that existed in computer science domain from 80s, which is a classical problem, like the mathematical problems that people may remember when we were high school students. Suppose that you have a village and you have Byzantine generals, and these Byzantine generals can talk with each other only if they see each other. Like there are fields, there are trees, there are obstacles, they may not communicate, and they did not have cell phones, okay? And, but if, like people in the village are also smart. They talk with the Byzantine general who's close to them. And that Byzantine agent can send erroneous and inconsistent information to its neighbors, to its Byzantine neighbors, right? What happens is that the other generals are kind of confused if that deceived Byzantine general is sending, let's say, do not attack the village at this moment because you may get fooled, you may get attacked, you may get deceived or trapped, and sends another information to another neighbor that, okay, it's time to attack, everything is prepared. Then they cannot decide. There are many scenarios that they cannot decide whether it's time to attack or not. That triggered a problem. Well, this is the way that we tell it as a story, but this was coming from an application in computer science. These were computers back in 80s. We didn't have internet in its current form and everything, and people were just wondering about binary consensus between the processors. So these were 0 or 1, and the purpose was consensus on 0 or 1. Okay. This problem called BGP or Byzantine general problem, people were tackling this problem like in 83. One of them was Professor Nancy Lynch. She was very young at that time. I talked with her with some updates on these algorithms that we made like in 1980s. But the reason that I brought this is that the algorithm that I'm presenting is type of relevant to Byzantine generals problem. But before doing that, maybe, so I'm not sure about like the audience here. So I start from some introductory notions in graph theory. You know that multi-agent systems are modeled as graphs, and graphs have nodes and edges. They communicate with each other with edges. And the purpose of a multi-agent system is to reach a global, usually global, uh, uh, point or global, maybe formation, global purpose. They have a global purpose. So they cooperate with each other, probably locally, without having the knowledge of everything to reach that global purpose. So these are modeled as graphs, but the graphs are moving. Everything is time varying and dynamic. Sometimes the graphs can be directed, means that if you talk with another agent, the other agent cannot talk with you necessarily. And one of the problems, which is probably the easiest one to think about, is to reach consensus, which is relevant to Byzantine general's problem. However, usually in multi-agent systems, there is no Byzantine agent. And consensus means the agent's value reach one, or they meet each other at some point. In robotics, people were seeing it as a rendezvous problem where robots were meeting at some point. But since we are not considering any dimension, any like size for the graphs or nodes, we just call it consensus, which is a general term. There are conditions to reach consensus with simple algorithms. You can find them back in 2005, maybe 2007. There were breakthrough papers that the necessary and sufficient condition was strongly connected when you want to reach average consensus of the agents, or it was having a spanning tree in the graph when it was a general consensus, not necessarily average values of the agent's initial value, okay? Strong connected was a key notion in topology of the graphs, which was coming again from the graph theory, but the philosophy behind having a strong connectedness, and give me a moment, I will introduce what a strong connectedness is, was that they wanted the information to be shared among the agents. Everything was good until like 2011 that people said, okay, these are so vulnerable to attacks and changes in the agent's values. And then like things started from actually a little bit sooner than that in Idaho National Lab, and it was coming faster and faster when Stuxnet attack occurred in Iran, and many other attacks occurred in the US and other parts of the world, and they also touched these multi-agent systems problem. They assume that some of the agents are designed. That means they send wrong or erroneous, inconsistent information to their neighbors. However, they are assumed to be sending consistent information, uniform information to their neighbors at each time. So things were just corrupting. The consensus algorithms were not working. So with that, we have two sets of nodes. We have regular nodes that are agents that are applying predefined control law, which uses local information to reach consensus, and they are oblivious of identity of other agents. They are just the regular agents that we used to have, okay? And we have Byzantine adversaries or malicious adversaries, which is a more general term. They are not sending necessarily inconsistent and non-uniform information to their neighbors. And those agents are applying control rules in an arbitrary way. They might be, at worst cases, adversarial and act against the consensus of the normal agents. Remember, when we were talking about fault, this was not the case. It was a random thing that was happening, but this is an intentional, maliciously behaving agent. We have more assumptions here. They are omniscient. I can give you a good term in Farsi that we say danai mutlaq. They are omniscient, which means they know all useful information from their network. They have active cooperation together, even if they are too far from each other. Okay. they can choose their updating time. They are anonymous and there is no signal or flag to identify them. Wow, this is just so hard, right? This is why cybersecurity is so difficult. And this was the case even before cyber physical security was coming to the table. They can send different values, different neighbors, to different nodes in the same time. But remember that we cannot be just this hard when we want to tackle a problem. We have to assume something that makes it tackleable. For that, usually we and this is coming from almost all fields, but it's also coming from robust control, that people just assume a certain bound on something, on uncertainty. Here, that bound is the maximum number of malicious nodes in its neighborhood or in the entire network. If it's in the neighborhood, it's called F local malicious model. If it's entire model, it's called F total malicious model. So far, nothing was new. The new part is actually a new notion called strong or robust. But before that, I have to introduce our reachable set. For a D graph, and D graph is directed graph, the subset S of its nodes is said to be R reachable if there exists a node in that set that all of there are at least R neighbors outside of that set that are connected to that node. It seems a little bit, hard at the first place to imagine, but it's just, having a node inside the set that have at least R incoming links from outside that set. That's it. It's actually more difficult to understand or define when we are talking about R robust graph, which is coming from R reachable set. A graph is R robust if for every pair of non-empty disjoint subsets of V, at least one of the subsets is R reachable. Okay, you have to consider all pairs that are non-empty and disjoint, and one of them at least should be R reachable. This was helping us in MSR algorithms in general consensus, not average. And averaging or average consensus is more applied thing to achieve. Is actually harder to achieve when you are talking about in cybersecurity. And with for that we went it was not working for our robust graph, and we had a good reason. We had good counter examples why it's not working. Then we were thinking about a strongly robust graph when a graph is called strongly robust if for any non-empty subset of nodes like S, either S is R reachable or there exists a node that node itself is connected to all of the neighbors that are outside that set. But this R should be at most half of the number of nodes. This is called strongly robust, and this was introduced not by us, by Sundaram. He's a student at that time as a subsection in a paper. They were talking about another algorithm, but we are using it for average consensus after I don't know 7 years or so. So in averaging, what you do is that you get the initial values of the agents, and the purpose is that those agents reach the average of the initial values. Let's say you have n agents, you are just have to sum up those initial values and divide it by, right? There are many applications of average consensus. And the good thing about average, one of the reasons that this has more applications than the general consensus is that the sum of the agents agreed upon value is the same as the sum of the initial values value. And we were seeing it in a power system problem that Dr. Bagai is going to talk about. I don't know if he's going to talk about multi-agent systems or not, but usually you have those assumptions a lot, like power of the system, energy of the system. Something is fixed, something is constant. And this was not the case in consensus, in general consensus, okay? Okay, this algorithm is coming from, it's part of, it has a history, basically. we had work on resilient averaging consensus, but they were using global information, which was like, which was related to like works that were trying to designing some like observers. They were trying to come up with the initial values, but it was not in a way that you feel that you have a like distributed algorithm. And these were, well, they were outstanding, great works that that were published in 2011, 2012. But the only bad part was that it was global. You had to design like observers that were seeing everything in the network. There was this algorithm that was used 2004, and then it was used again in communication systems, in robotics systems in 2012 as a certified propagation algorithm. Well, people were caring about propagating a value to a network. Okay, but when you have Byzantine nodes in the network, probably that's harder, and people were using this algorithm. But what we did was we used this for resilient average. The algorithm is so simple. I mean, I can give you. We called it Sabah, which is also like a term in Farsi, but it's secure accepting and broadcasting algorithm. But the idea is so simple. Like as a node I, you broadcast your value to your neighbors, and your neighbors also do the same. And this happens again and again. And as a neighbor, as a node who is receiving these values, you have to accept or reject the values that you are receiving. You accept it if you are receiving from more than or from at least f+1 incoming neighbor. So it's like a majority vote. If you have f+1 incoming neighbors that are sending same information for a value, for a labeled value, let's say node I, and you are node J, and you are receiving f+1 same value for node I, then you are accepting that. If you are not, you don't accept it. And that's because probably in the way from node I to node J, there are more, or there are Byzantine agents who are just messing with node I value, and they are sending wrong information to you, and you don't have to do it. Okay. This is the case also for asynchronous updates. Things like there are some details here that you can check in the paper. I'm not going to go to the math deeply here, but I gave you the idea, and you feel free to ask questions when if you have some thoughts and concerns here. Resilient averaging is then very simple. When you accept those trusted initial values with that majority voting scheme, then you just make an average, right? We just smoothen the average. We just have a smoothen the averaging here with some terms, but these are not important at all. They are not playing the role in the proof of the algorithm. And the theorem becomes like regular agents will retrieve I0 and achieve resilient average consensus by executing Sabah or asynchronous Sabah for at least k bar steps if the condition graph is strongly 12+1 row. So this is not a necessary condition. This is just a sufficient condition. And necessary condition for this algorithm, at least was not trivial for us at the moment that we were writing the paper, and still we don't like. There are necessary conditions, but it's not quite sufficient. And we can prove that necessary condition cannot be 2f+1. Okay, that's also something we know. Question: we have connectivity, 2 connected, 3 connected, k connected. Mr. Sharif, you like? I think I talked about like 24 minutes now. How much can I go further?
I think you have 10 minutes.
Okay.
Do you hear me?
It's fine. I try to wrap it up in 5 minutes so that like people have time to ask questions. And sorry, I don't see the chat. If you are writing something, I don't see it, but after the presentation, I can talk about it. Okay. One of the examples is wheel graph that you have 6, like in this case, consider you have a wheel graph with 6 nodes. And what is a wheel graph? You have a center node, and all other nodes are connected like the way that you see the wheel of bicycles, like bikes, okay? And they are like the other nodes are also connected in a circular way. This graph is 2f plus 1 connected. Like in this case, it's 3 connected, but it's not strongly 3 robust, okay? So you have examples of 3 connected graphs that are not strongly 3 robust. But to be more precise, and why this is the case, let's look at this example. And I like giving the examples because it's more tangible than just giving scheme of proofs here, okay? Node I is sending its initial value to its neighbors, 2 and 5. And node 6 is Byzantine, okay? And then in the next time step, node 5 is sending the initial value of node 1 to its neighbors. One of its neighbors is node 4. Node 6 has also received initial value of node 1. But since it's Byzantine, it can send inconsistent initial value to its neighbors. Let's say changing A to B, and B is not A, okay? B is not equal to A. And sending C to node 4, and C is not equal to A, or at least is not equal to B. So that means Byzantine node, okay? And node 2 is also sending A to its neighbors, which is 3 in this case. Now it's turn for node 3 and 4, and they are receiving 2 values, and they don't have any other value to decide. If they had like 2 A's, they could say, okay, we have 2 A's, 1 C, probably A is correct. Or also on node 3 or node 4, okay? If you have 2A and 1B, probably A is correct. But this is not the case. They cannot use majority voting here. The graph is 3 connected, but it's not 3 robust, and they cannot decide which value is correct. So they cannot do the average. That was the essence of the proof and the sense of the intuition that we had behind this paper. Okay, I can talk a little bit about some graph theory notions here, why connectivity is connected to robustness and how. We have identified 4 connectivity notions in directed graph theory. One of them is strongly connected if for every pair of nodes they are mutually reachable. The other one is unilaterally connected if every node can either reach or be reached from every other node. So it's not two-way, okay? The other one is weakly connected when may not be unilaterally connected, but if you just remove the direction on the edges, what is remained, which is a not directed graph, a simple graph probably, is just weakly connected. And disconnected is that none of this is true. None of these holds, okay? We call disconnected as C0, weak but not unilateral, C1, unilateral but not strongly connected, C2, and strongly connected as C3. And a strong connectivity of a D graph is actually the minimum of 3 values, basically. And we have to define another like connectivity notion here called Kij. Kij is the minimum number of nodes whose removal changes D from a D graph in the category of Ci to 1 in category of Cj. For example, if J is 0, then that means that you are changing the graph from weakly connected to disconnected, okay? Usually Ki0 is the Kg, or is denoted as Kg in graph theory, but a strong connectivity level is the minimum of K30, K31, and K32 when you want to traverse the graph or change the graph from a strongly connected to unilateral, to weakly connected, or to disconnected. That notion, when you minimize these 3 notions, this gives you the strong connectivity level. Okay, with that, I mean, there are details that you can check in the paper about this notion and how it's relevant to the proof of this theorem. But the graph D is strongly or robust. And when you have that graph, then you know it is also strongly R connected. I think that's a very good result. You have this one-way result. If it's strongly R robust, it's strongly R connected. It is also R robust. It is also the case that the minimum number of edges, the minimum number of neighbors for each node is at this R. It is also strongly R prime robust, where R prime is less than R. If it's 3 robust, it's 2 robust. Removal of k incoming edges from each node of D makes it strongly R minus k robust. We have other results in our previous papers related to R robust and R connectivity. And I don't want to go to the details, but it can be proved with connecting this theorem to other results that the graph is strongly one connected if and only if it is strongly one robust. So if the R robustness level, if you are talking about one robustness, it's tied, or it's equivalent to having the one strongly connected graph. And very interesting result is that when F is 0, it means that there is no malicious agent, because F was the maximum number of malicious agents. The necessary and sufficient condition to achieve average consensus in directed graph with this algorithm is strongly connected of the communication graph. This result, interestingly, I mean, this is for non-cybersecurity case, okay? But it was coming like after 5-7 years after the first paper in average consensus. I think it was first in 2012 that this result came up. But one of the I believe good reasons, or maybe if you want to make yourself or put yourself in a very hard situation, is that to start from the cybersecurity case. If you solve the problem in that case, you have a lot of intuitions and a lot of results in the case that you don't have the attacks. And this was the case here. People were tackling this problem for 5-7 years, but it was just solved when you had solved it for the case that you have attacks in the network. This is an example. Here is a 3 robust graph. But if the node 3 and 5 are connected to each other, if you remove that link, which is like a bidirectional link from 3 to 5 and 5 to 3, then the graph is 3 robust, but not 3 strongly robust. And I'm just, I may ignore strongly here because we don't have non-strong notion here, okay? Then what happens is that you apply the same algorithm, Saba algorithm, and you don't reach the consensus. You don't reach the average consensus. And here the initial values are exactly the index of the values. That's just to make it simple. Agent 6, for example, has value 6 and so on and so forth. And you see that agent 4, which is the malicious agent, is behaving differently, not very complicated, by the way. But with this simple behavior, you see that agent 5 is just isolated and different in location from other agents. So that's one of the reasons I said that the necessary condition is not easy to achieve. But this is an example that just validates, and not proves, of course, this is just a simulation, that our sufficient condition is working. You had a 3 robust graph, you had that link in its place, 3 to 5 and 5 to 3, and you see that the average consensus is achieved. This is another example that we didn't talk a lot about, like a synchronous case. What asynchronous means that the agents are updating at different times with some delays probably in the communication. The intuition is not different, and you reach the average consensus with synchronous Saba. Okay, as a conclusion, we introduce a novel approach based on CPA for the problem of distributed averaging, where the dynamics of the agents and the weights are not involved. We didn't involve any weight of the algorithm. That's also another thing that is a benefit. The weights can be also time varying or changing. The connectivity required for the consensus becomes denser than the existing literature, but the algorithm is fully distributed and can be easily applied. The sufficient condition is a strongly 12+1 robust for F local Byzantine nodes. Everything was local, which is great. F local is actually more distributed notion and definition. We proved some of the properties of a strong robust graph, such as their relation with strongly connected graphs. And in future, these algorithms can be applied in different applications, such as power systems. And that was one of my motivations to apply this in power systems. We actually have one of, not exactly this idea, but somewhat similar with retrieving the initial values in wide area control systems that we use the connectivity notion or connectivity approach back in 2018. With that, I'm going to conclude and let the stage open for questions if there is any. Thanks for your patience. Okay, there is no question, at least in the chat. If you have, I mean, with authorization of Dr. Sharifi, I wanted to ask if there are questions and you think that it's a little bit hard to say it in English, just feel free to type it or say it in Farsi. Okay. اگر یکی از نوت‌ها از مورد حمله قرار بگیره و اطلاعاتی نفرستاد و نگیرد، تو این روش چه کار باید کرد؟ Okay, this is yet solving the problem as well. This is a very good question, because when you don't have information, that's considered like as an empty or not receiving a value. Then the majority voting just assumes that this is coming from a Byzantine path, and call it Byzantine path, because normal agents usually do that. Okay, and we assume that they do that. So it's just obvious that if then you have F+1 in consistent and uniform information from other paths, then you can use it. So it doesn't impact the algorithm at all. Can we design an attack prognosis system like what we have in fault problems, which leads to some predictive recoveries? Instead of waiting for presence of effects of attacks, if yes, are the predictions for future of system or signals are reliable? This is also a good question. I'm not sure if I understood it correctly or completely. It seems that Mr. Mehranfar is thinking about looking at the problem from fault detections perspective, and he's wondering if we can do some predictive recoveries. And correct me if I'm wrong, Mr. Mehranfar. I think yes, of course you can use. Well, the first papers that came out in cybersecurity were all using fault detection and isolation algorithms, FDI. And there is a good dissertation back in 80s by an Iranian scholar. He's actually in Sharif University now, which was published in MIT. And people were using that dissertation a lot. But the main difference is there are two differences, or sometimes people say just one difference, is that you have to know the model of the knowledge or something about the model. If you know that, then your attacks or your faults are smarter. You are trying to corrupt something. This is not the case in fault. In the fault tolerant problems, you are assuming something is corrupted. You don't know why, you don't know how, you don't know, and you are trying to detect that. So it's like detecting the fault, which is random, probably, right? So you are limited a lot by those easy assumptions. So I would say the definition, you should be very careful when you when you generalize your definition from fault to attack, and you see that solution is also working for that definition, you should be very careful. Sometimes those solutions are not working when you assume something else. One of the papers that was introduced, I think, by forgot, maybe one of the presentations was like introducing the paper that was talking about modeling attacks with knowing the system knowledge. So that's a very important paper. If you look at that one, there is a matrix that like the authors Teixeira and Henrik Sandberg, they were just assuming how much knowledge the attacker has about the system. In fault, there is no knowledge that they know the faulty node or the faulty agent knows about the system. So you should be careful about that. I think you can ask a question by voice. Yes. Still, I don't hear anything.
Greetings. Do you have my voice?
Yes.
As you actually presented about cybersecurity, as you know, we are passing this industrial revolution and going to the new one. And as you know, the more the industrialization and technology improves, the more the attacking ways are improving, and they are going to be much more complicated and much more improved. What's your opinion to use quantum technology? It's actually properties like quantum key distribution in communications and these kind of things to have much more secure, actually, cryptography, because it's common in the societies that say the only way to hack quantum computer is to have its password. Which means that it's so hard to hack a quantum computer, but there's a way to hack it by another one that they are so expensive. What's your opinion to use quantum method, actually quantum-based particles, something like quantum key distribution to have much more secure communication?
Okay, so I'm not aware of quantum distribution. Maybe it's a technical term. Sorry for my lack of knowledge here, but quantum computing is the way to go for cybersecurity, and I can assure you that's the case. But it's actually a double-edged sword. It's also available. When it's available for you as a defender, it's also available for the attacker. It's good for you as a defender because, as you said, you can have passwords that cannot be, that there is depending on the length of the password, let's say in your Windows, there is a time that attacker can retrieve your password. And you can increase that time a lot with quantum computers or quantum computing or quantum computations in general. And in cryptography, as you said, also it is applied. In general, you have I don't know how to. It's just so scary when you have those quantum computers in place. I don't know when, but it's just so faster, right? A lot faster. So it's easier to detect. Everything is easier. And I would say everything in computational world is easier. Like AI is also very different. Cybersecurity is different. So yes, but when you have them available, you can use some algorithms, of course, here, but since you don't have quantum computers, I don't know how efficient or how things are getting better, in a meaningful way. If I have understood your question correctly. By the way, I noticed that I announced that you can ask questions in Farsi, but I said that in English. So اگه سوالی دارید به فارسی هم میتونید بپرسید. یعنی بگم که اگر کسی سوالی داره میشه این روش رو برای رندوم گراف توسعه بدیم؟ بله، چون رندوم گراف و پایداری وابسته به نوع گراف رو حذف میکنن. البته این ببینید رندوم پایداری وابسته به نوع گراف، ببینید این جمله دومتون نوشید به نوعی، دقیقاً به نوعی واقعا. یکی از کارهای خیلی خوب کلا اینه که اینا رو ببرید سمت رندوم گراف، ولی منتها باید یه دقت بکنید که اینا یه اپلیکیشن خاصی دارن. شما هر گرافی که هر مسئله رو نمیتونید به صورت رندوم گراف مدل بکنید. خب مثلا مسئله خیلی فرض کنید حالا رندوم اردوشرینی گراف رو در نظر بگیرید که خب مثلا هر یالی با یه احتمال وجود داره یا نداره، مثلا با یه برنولی پروسسی وجود داره یا نداره. خب این یه سری مسئله خاصیه. یا مثلا یه سری رندوم گراف هست، مثلا آر رگولار رندوم گراف، نمیدونم جیومتریک رندوم گراف، مثلا تو روباتیکس خیلی میتونه کاربرد داشته باشه. دقت بکنید که اپلیکیشنتون رو دارید خاص میکنید. ولی یه اتفاق خیلی خوبی میتونه بیفته اینجا. این نوشنای خیلی حالا تو دنیای فازی که من دوران فوق لیسانس کار می‌کردم میگفتن کریسپ، خیلی تعریفای کریسپ خیلی خشکیه. اگه اینا رو بتونید مثلا با یه چیز پروبابیلیستیکی رندومایزی ترکیبش بکنید، یه سری ریزالت خیلی خوب میگیرید. یعنی من پیشنهادم اینه که یا حالا گراف اگه رندوم بشه میگم اپلیکیشن تو محدود میشه، ولی این الگوریتم‌ها رو رندومایز بکنید in a way که ما البته این کارا تو 2018 یه اپلیکیشنی انجام دادیم یه چیز شبیه، و خب یه سری کاندیشن رو تغییر میکنه، نه لزوما رندوم گراف یه کاری هم البته 2015 actually تو IEEE TCNS Transaction Control of Network System چاپ شد که کار خیلی خوبی بود که اومده بود گفته بود این خود روباس گراف رو البته گفته بود که مثلا اگر که n که number of nodes تعداد نودها بره به سمت بی‌نهایت، میل کنه به سمت بی‌نهایت، او وقتی یه سری این کاندیشن‌های روباستنس و کانکتیویتی معادل میشن. خیلی نتیجه جالبی بود. ولی خب میگم این مال اپلیکیشنی که رندوم گراف استفاده بشه. خیلی گراف توری دی پی شما لازم دارید اگه بخواید این کارو بکنید. درس گراف توری زیاد خیلی باید عمیقاً گراف توری کار بکنید. آقای کیوان نمیدونم آقای شریف ما تا کی وقت داریم؟
Dr. Dibaji, the time is over.
Okay.
And I should inform you that we are behind the schedule. Thank you, Dr. Dibaji, for good presentation you provided. And I want Dr. Bagai to continue the discussion. Dr. Bagai, we have about an hour to finish the workshop, and the room may close automatically at the end of 3 hours. So please manage your talk. And because there exists nobody outside Iran, we can have the Q&A at the end of the presentation in Persian. Okay? So Dr. Bagai, the floor is yours. Thank you very much, Dr. Dibaji, again.
Thanks.
Hello, everybody. Can you hear me?
Yes, but we don't have your camera.
I think you... Yes. Let me check my camera. I think you have now my camera, yes?
Yes, I can see you. The floor is yours,
Okay.
Dr. Bagai.
Thank you. Thank you so much, Dr. Dibaji, Dr. Sharifi, Professor Talebi, and Ms. Behnia, and Ms. Firuzman for their great presentations. In the final part of this workshop, we discuss about cyber resiliency and data-driven management aspects of conventional and power electronic-based power systems. I am Hamidreza Baghai, an associate research professor of Electrical Engineering Department in American University of Technology, the Center of Excellence in Power Engineering in Iran, and the pioneer of sustainable development. I briefly introduce myself, and I try to manage the time. As I said, I I am an associate research professor of electrical engineering department in AUT, the winner of 4 national and international prizes for my PhD dissertation. That honorably I passed this dissertation under advisorship of Professor Talebi in AUT. From Iran Scientific Organization of Smart Grids, Iran Energy Association, American University of Technology, and IEEE Research Iran section. Highly cited researchers of Web of Science and listed in top 2% of scientists in the field of energy based on the Stanford University reports published recently. I'm also the project coordinator of AUT Pilot Microgrid and another project for design and implementation of microgrids in NERU Research Institute. Also, an associate editor of IEEE Journal of Imaging and Selected Topics in Power Electronics and IEEE IET Journal of Engineering, a member of IEEE Iran Section Communication Committee and some subcommittees in IEEE PES, such as Transmission and Big Data and ICRoM. In this presentation, as an outline, I review some basic concepts for those that are not enough familiar with some concepts in power engineering in smart grids that always power engineers learn in the university or experience in the industry. In the second part, I explain about the concept of energy internet and internet of microgrids and some fundamental motivations that force us to follow this cybersecurity issues. And after that, about data-driven management and the necessity of cyber security and cyber resiliency. And finally, the whole framework of cyber resiliency will be discussed. If I'm not sure, but hopefully, if we have much more time,
Dr. Baghi,
I can.
Dr. Baghi, do you hear
yes.
me?
Yes, yes, yes.
Can you please change your screen to full screen mode or no?
I share, this is full screen.
No, we are seeing it in the, we are seeing not in full screen mode, in the normal mode. Maybe you see something else in your monitor than what are we seeing in the screen of the ICRoM.
Let me check again. Is it good now?
No, it's not still. Oh, yes, yes.
Yes. Okay.
You are in the page number 6, okay?
Yes, yes, yes.
Is it right? Okay.
Yes, yes, yes.
Thank you.
And finally, if I'm not sure, but if we have much more time, if have enough time, I can provide some applications and examples. If we have not much more time, you can follow these concepts in my recently published papers, especially published in the period of 2018, 19, 20, and 2021. And finally, I provide some important references of our papers. First, let us discuss about the fundamental terms. You know better than me the conventional power systems, but the concept that is really increasing in the literature is power electronic based power systems or power electronics dominated grids, PEDG. You know, we experience larger scale power plants in distributed power systems, and in recent years, They are moving, the power industry is moving to distributed generators, as we experienced in most part of Iran. We are moving from the central power energy management to distributed and decentralized control. And of course, we experience in some countries, not surely in Iran, in some countries like Germany, like USA, to the trends that will lead to 100% renewable energy generation and integration of renewable energy, especially of ones who named variable energy resources, and integration of utility scale energy storage systems, and utilization of microgrids, HVDC, MVDC, and recently electric vehicles. This is the framework of a power electronic dominated power grids, including the microgrids, the red circles, MVDC and HVDC networks, and charging stations of electric vehicles, and some parts in LV side, in AC and DC microgrids. The power converters underpinning technology for power system modernization. A power electronic based power system almost has three basic layers. I mean decision, communication, and coupling, and physical layers. And in this block diagram, we can see that in different parts of a power electronic based power system, we experience the power electronic converters. For example, in wind generation units, in solar panels, in MVDC, HVDC, transmission and distribution systems, in electric vehicle charging stations, and so on. We experience some challenges in conventional power systems. For example, in planning stage, we experience facility planning, seasonal, day ahead or weekly planning and operation, and intraday one. And we face some issues regarding the adequacy in generation, transmission, and distribution level in different hierarchy levels. And in operation, the major concern is almost security in deterministic and probabilistic manner, and also from the dynamic and static viewpoints. In static, we concerned about the voltage limits and thermal ratings of the lines, and in dynamic security assessment, we experienced some issues regarding the voltage stability, angular and frequency stability. In modern power electronic dominated grids, we experience some issues more than ones we show in previous slides, such as microgrid operation, renewable energies, and power electronic converters, and different aspects of, for example, in power electronic, protection, reliability, and converter interaction issues are major concerns. In renewable energy, we concerned about the security and adequacy, and in microgrid, one of the aspects that we concern are cyber security. That is the major topic of this presentation, and of course this workshop. Then the challenges that I present regarding the conventional power system should be modified for power electronic dominated grids. Let us go to some more definitions. The nature of a power electronic dominated grid differs from conventional power system because they have much lower inertia and almost stochastic generation nature. I mean, such that we experience in photovoltaic and wind energy generation, multi-time scale dynamic behavior, generation unit and load proximity, almost in distribution systems, and balance and nonlinear loads, and of course low amount of feeder reactance to resistance X to R ratio and low short circuit capacity. In this situation, for power electronic based power systems, the concepts of stability, categorization, and vulnerabilities and analysis of power electronic dominated grids are required to be reassessed and rewritten. Just to remind, we have recently published a book, Microgrids and Methods of Analysis, that recently has been selected as the book of the year in Iran power industry, and reassess these concepts for modern power electronic based power grids. In power electronic dominated power grids, we employ photovoltaic, wind, battery energy storage system, HVDC and MTDC microgrids, and of course charging stations of electric vehicles. I should emphasize that a PEDG can be interconnected to a large power network through a point of common coupling, and of course can have three different control layers as we present in next slide. I mean primary, secondary, and tertiary control. Another definition that we should note is for microgrid, based on a definition, a microgrid is a small-scale power grid in low voltage LV that must be able to locally solve the energy issues and enhance the flexibility, and can operate in grid-connected and islanded, autonomous mode of operation. We have some basic challenges in microgrids, such as power management, control, and protection issues. Also, we should discriminate for conventional power grids, microgrid, and nanogrid. I mean nanogrid such as developed in IIT, Illinois Institute of Technology, as a sample, is a low voltage grid that typically serves as, for example, single or multi-building. Next, we can provide a framework based on IEEE standard 1547.4 and include the operation modes, storage units, distributed generation, and power converter interfaces. This is the whole framework of a microgrid based on standard definition. In both modes of operation of a microgrid, the microgrid, or in a general concept, a power electronic dominated grid or power electronic based power system, is subjected to different small and large signal disturbances, different nonlinearities that sometimes comes from nonlinear dynamics of some distributed and renewable energy resources, such as photovoltaic, battery energy storage, wind generation units, wind turbine, and something like that. And of course, a variety of nonlinear loads. And of course, is subjected to topological, parametric, and communication uncertainties. As presented in the previous lectures, resilience is intrinsically complex property that requires deep understanding of operation of the whole system. And we name some system to be resilient, for example, a microgrid or a power converter-based power system to be resilient if a resilient microgrid or power electronic dominated power system shall have enough robustness against all mentioned disturbances, nonlinearities, and uncertainties. If we have enough robustness for small, large signal disturbances, nonlinearities, and different kinds of uncertainties, and sometimes attacks, we can make the system resilient, and we can name it as a resilient system. In this presentation, something that we name cyber resiliency mean that the system has enough robustness to keep its stable operation and performance in the case that the system is faced to these disturbances, attacks, and some uncertainties. Next. We have some standards for communication in microgrids. I mean, IEC 61815, and different extensions of this standard for hydro and distributed energy resources and wind turbine and wind plants and other kinds of system. And there are some basic differences between existing and conventional grids and intelligent or smart grids. For example, we have electromechanical parts in existing grids, and in intelligent grid we experience digital one-way communication to two-way communication, centralized generation, distributed generation, hierarchical system, network-based control system, and so on. In the next part, in the second part of my presentation, I should talk about the conceptual Internet of Microgrid. Before that, we should review the definition and conceptual IoT, Internet of Things. The Internet of Things is a name for aggregated collection of network-enabled devices such as PCs, traditional computers, laptops, and some other devices that may include Wi-Fi connection, Bluetooth, or other medias, or sometimes NFC, near-field communication, and can include some devices like appliances, home security system, computer peripherals, webcams, printer, and wearable technologies such as Apple Watch and so on. And it can connect devices for many applications. By the way, the IoT devices and IoT-based systems work based on the concept of Internet Protocol, I mean of IP. The goal behind the Internet of Things is to have devices that self-report in real-time manner to improve the efficiency and bringing the, important information to the surface more quickly than we experience than a system depending on a human intervention. Based on a definition, energy internet, based on the definition of IoT, energy internet refers to a combination of advanced power and electronics-based technology, information technology, and intelligent management technology that and a large number of power network, petroleum, gas networks, and distributed generation or renewable energy generation units, distributed energy storage, and a variety types of loads and metering devices. In using the IoE, Internet of Energy, we can upgrade the automating our electricity infrastructure for energy producers and manufacturers, and help to to have an increasingly prominent market in power electricity market. By the way, in this manner, the power network and transmission system and generation system can be more productive based on the concept of energy internet, like we experience in information internet that connect some computers, laptops, and so on together. Using the energy internet, we can connect based on some infrastructure or communication. We can connect the generation units, solar panels, electric vehicles, and other devices and subsystems in a power grid. Yes.
Do you hear me?
Yes, yes, yes.
Sorry for interruption. Can you please click on the hide link near the stop sharing button?
Yes. Yes,
Thank
sorry.
you very much. Thank you very much. Continue, please.
Thank you, thank you. Using the concept of energy internet, we remember that we were moving from local investor owned based electricity utility to legacy centralized power system, and after that to a smart grid, and in the near future, as we experience in some countries now, we are moving to energy internet. This is the trend of evolution. In this concept, we provide, based on the energy internet, we provide energy energy infrastructure. That is the basic requirement for having smart cities. I mean that if we want to realize a smart city, we need to first develop the concept of energy internet inside this smart city. Using AI, we have some layers, I mean technology layer, market layer, and information layer, that in this picture, all of them are connected together to have a power flow between different parts, smart loads, electric vehicles, utility grids, and electric vehicles, to the control system of the whole microgrid, renewable energy, and they are connected together from some medias of information flow shown in blue. One of the basic necessities of energy internet concept is development of Industry 4. You can see the Industry 4 framework as explained in the presentation of Dr. Sharifi. In Industry 4, we experience big data, augmented reality, cloud computing, cybersecurity issues, Internet of Things, and some other parts that provide better sustainability, awareness, and comfort-oriented customers' behavior. In this manner, we can develop this concept to reach to the Industry 5 concept, as explained well by Dr. Sharifi. And if we review, we experienced in the past years, from the first to fifth generation of the industry, from mechanization, electrification, automation, globalization, and finally personalization, that we experience in Industry 5. As a better illustration, I think we're moving from hunting society to agrarian, industrial, information, and in the near future, super smart society, by moving from Industry 4 to 5. And there are some basic differences as explained. I move quickly because explained well, better than me, by Dr. Sharifi. By the way, using the concept of energy internet, we have some social impacts that provide some sometimes better welfare and satisfaction for the customers, for the people living in the society, to have the maximum flexibility in the power, in the information layer. For investigating the social impact of the energy internet, I should mention that number of connected devices per 100 inhabitants in different countries have been compared here. For example, in the top of list, we have South Korea, after that Denmark, Switzerland, and USA, and finally we experience, for example, Turkey and India and Russia in the downside. Some enabling technologies we require for realizing the concept of energy internet. The first of one is centralized, decentralized, and distributed control structure for energy internet. I mean that a set of sensors and actuators in the control system that make some commands to make some changes and some events in power system, and this set of sensor actuator gets some commands from RTUs and PLCs, and in the upper level, SCADA, supervisory control and data acquisition system. In this framework, you can see another viewpoint of microgrid supervisory control and energy management system, that in downside, we have local controllers that make some commands to the distributed energy resources and connected loads and PCC. And in the upside, we have the supervisory layer and other layers that can control the whole microgrid. For better illustration, look at these diagrams. In these diagrams, the SIGAN parts are sensor actuator nodes in different parts of the plants. The black one are communication, almost two-way or one-way communication. The blue is controller, and the green sides are communication network. In centralized control system, one controller, the blue circle, can control the whole plant. In the decentralized control, each part, each set of sensor actuator node and each part of the element, the controllable element, has its own local controller. These dots, these squares, blue squares, are each one local controller that are connected together in decentralized manner, in distributed, almost working based on the graph theory as we as explained by Dr. Dibaji in the previous presentation. And finally, in the hierarchical level, we experience different layers that each of them can be work based on centralized, decentralized, or maybe distributed protocols. And finally, one supervisory layer outside control the whole system and make some and send some set points to the downstream layers. By the way, we review the different parts and enabling technologies that are required for realizing energy internet, and most important part is solid state transformer that can provide enough flexibility. You know, in communication internet, in LAN and WAN network in communication, we have some routers that connect some computers, laptops, and other devices to the internet and a network. In energy internet, we need some power and energy routers. In these energy router can be realized by making a solid state transformer, including some power electronic component that can provide the flexibility of transferring power from different parts of a microgrid. For example, electric vehicle charger, PV, storage units, and other parts. And this is a single line diagram of, for example, one solid state transformer, including AC-DC rectifier, DC to DC converter, and other power electronic based modules that can transfer energy in AC and DC sides and provide enough flexibility for the whole whole microgrid system. In another illustration, we may experience these solid-state transformer, I mean power electronic-based converters in different parts of a power grid that connect AC and DC parts and loads generation unit in different parts, and sometimes can realize MVDC or MTDC, I mean multi-terminal direct current grids. And one other parts of this energy internet framework are electricity markets, including the generation companies, energy companies, transmission system operator, and distribution system operator that all of them form an electricity market. In each part of this electricity market, when the signals are transferred from a supervisory layer to a control unit, in each of them we may have some cyber attacks, and we should think about the resiliency of the whole system in this part. The energy internet, the energy internet reforms have happened in USA, Germany, Netherlands, Japan, and China in recent years, and they started providing the energy internet and internet of microgrid for better flexibility and satisfaction in the community and realizing the smart cities. This is the trend and time frame of this development, and I think as expected, in 2050, we may reach to near full development of transactive energy in different regions. I mean, in the energy internet, we have transactive energy trades in electricity markets, and we go to modernize the existing electricity infrastructure. By the way, this is the framework of electricity market that almost based on demand response programs and some price-based and incentive-based solutions that work in real-time manner for better satisfaction of the consumers. By the way, we review again the basic enabler technologies such as price information, device state, and other required information to a transactive energy agent, and finally go to the market. In each parts, we may experience cyber attack, and as I present in next slide, we may see that what is the outcome of cyber attack in the performance of whole electricity market. For better securing the energy internet, we may have some definition for cybersecurity that are required and mentioned as the requirements of various security measures and digital signatures, such as authentication, confidentiality, integrity. As mentioned in the previous lectures, we are some basic definitions for communication-based cybersecurity issues. In different parts of the energy internet, we may have some cryptography for ensuring the security, some secret key cryptography and public key cryptography that's sometimes mentioned as symmetric or asymmetric key cryptography. In this picture, you can see the differences between both of them, symmetric and asymmetric cryptography, so that the public key, we have some public key for encryption, and also some special secret key that is owned to one specific agent in the energy internet. We may use, as I think questioned by one of the audiences, we may use the quantum-based cryptographies based on SKD and QAD, symmetric key cryptography, and of course public key cryptography and quantum-based key distribution that may ensure the security of whole system performance. Because we have not much more time, I quickly go to next slide and illustrate based on some concepts that we should experience in the power system. By the way, based on the concept of energy internet that I explained, we should generalize this concept for energy internet of microgrid that we name ICRoM. And a smart energy system is an important open area of research for application of IoT that mainly work based on the application of distributed network-based control system. And the emerging energy internet and internet of microgrids are complicated based on the operational requirements of communication infrastructure and data interoperability systems. For developing a pilot and deploying a reference architecture for massive multi-party data exchange of the management and real-time processing of the energy in the energy sector, and providing some reference architecture in an open modular data analytics toolbox, we may define and experience some concepts in innovative energy services integration of relevant digital technologies like IoT, and use some AI, artificial intelligence, and machine learning algorithms and cloud-based computing and big data analytics services that all of them necessitate a unified data-driven ICRoM framework. Before defining this general framework, we should explain some details about the wide area control system. In wide area control system, we try to respond the real-time requirement of the power system in a large, vast, geographically developed power system, and based on different levels of criticality, we may improve reliability, stability, and guarantee the power quality for satisfaction of the different loads and consumers based on bidirectional flow of power and data in a wide area control system framework. The communication backbone of smart grid in wide area network will connect all parts of this grid based on some measurements and control actions that may happen in the grid in distributed fashion, almost distributed and network-based fashion. In the energy internet, we have we have a wide area control system, some data collector, and some connections into the system that each of them can be a special microgrid or power electronic dominated power system. In each of them, we may experience a whole control framework for each power electronic dominated or sometimes microgrid units, including the generation shedding, load sharing, and some other control mechanism that is related to all local controllers or DG and DES distributed energy storage units based on some hierarchical control system that I explained in the previous slides. In the EIOM, in the Energy Internet of Microgrid, the communication is mainly based on three different purposes. Communicating the meters, the meter readings to the control station, of course, and the distributed real-time measurement data, and finally the control message passing. In this situation, we may use a cloud-based network that receives data in real-time manner and provides some data collection that form a real-time data collection unit, RTDCU, as well as a smart meter. And decision will be taken in the cloud-based based on the collected data. I review the concepts that in this slide, I review the basic concepts that necessitates to have enough focus on the concept of big data. After making decision in the cloud-based system based on the collected data, we have some central loads, data collector, as we shown in this picture, and process the measured data and some signals based on a real-time manner and some bidirectional communication system. And the cloud will be a collection of computers and wide databases housing RTDCUs and smart meter data, AMR or PMU. AMR is automatic meter reading in the smart system, and PMU, as you know better than me, is phasor measurement units that installed in different parts of a power system. That will collect all information from the grid and process and generate the control actions. In another illustration, we can show the basic cyber-physical architecture of cyber-physical microgrid. It should better to say that cyber-physical co-multi-microgrid, because we have different parts of microgrids working in AC and DC voltage levels and connected together from power lines, power converters, and of course connected to the cyber layers through communication medias. The basic question in the final part of section 2 is that we should review this sentence again. The cloud is a collection of computers and databases housing RTDCUs and smart meters, AMR or PMU, that will collect all information from the grid and process and generate the control decision. With large amount of these information, the question is, what is the processing algorithms? These are the motivation to have big data analytics in this framework. As you can see, I should illustrate in this PDF. Can you see the PDF I show? Dr. Sharifi and all, can you see this framework in PDF?
Yes, we can see the PDF too.
Okay. In this, this is because the picture is very large. I decided to show it in PDF. We have a wide area control and operation level in the top layer, including engineering workstations, redundant SCADA servers, and front-end engineering processors, some firewall for security, and some operating stations, data control, and real-time simulators that may get some signals from the wide area control system. Finally, based on the data collection that we provide in this big framework, we have a big data processing module based on receiving some data centers, data collectors inside the wide area control system. And data is coming from historical data, for example, the trend of power consumption, the trend of power transfer in different parts of power system, weather situation data, for example. Sometimes we need the weather situation for load forecasting and other activities. And some other big data sets that may apply to this system and perform some data mining action, data-driven techniques such as data identification, redundancy identification, missing value processing, abnormal value processing, skewness, and data discretization, and standardization, and attribute construction. In these parts, the major module is false data detection, because if we receive some false data in the whole system, the performance of upstream wide area and downstream Internet of Microgrid, as we experienced explained in a previous slide, will be affected. These data analytics framework will be connected to the Internet of Microgrid based on some IEEE, IEC communication protocols, gateways, internet switches, gateways, and other communication devices. And these framework from the down to top will form the whole wide area control and measurement data-driven framework. Let us back to presentation. So the question that I asked, we try to address this question. In big data processing, after technological revolution, large volumes of data are incorporated to the process of generation companies and customers. Big data analytics refers to large volumes of received data from gateways consisting of different categories of weather, power grid, measurement, microgrid, and other signals that need a framework to process all information effectively. All of these data are imported to a cloud via data gateways and then managed to some steps of data mining actions, such as data integration, cleaning, transformation, and of course, false data detection. For cyber layer, we should focus on communication protocols and cyber security issues. Cyber layer and related communication protocols are important because microgrid control architecture inherently rely on tight coupling between the cyber and physical layer. If any attack happens in this data transfer system, the performance of whole system may be affected. We should have some protocols for bandwidth and data transformation and data transfer between different parts of the power system, working based on IoT. That the best standard for this part is IEC 61815. In the cyber layer, the basic challenge will be the cyber security, and the main purpose of cybersecurity is to ensure three major concepts: to ensure confidentiality, as presented in the amazing presentation of Professor Talebi in one of these slides. The main purpose of cybersecurity is to ensure confidentiality, integrity, and availability, briefly abbreviated CIA. our data and services. In cybersecurity definition, we have different, we have three basic concepts. I mean, integrity, availability, and confidentiality as we defined. And the key terms are vulnerability, threat, exploit, and risk. The vulnerability is a flaw, weakness, or error that can exploited by an attacker. Threat will be an event, neutral or man-made, able to potentially harm the computer system and organization or whole system performance. An exploit is a specific way that take the advantage of vulnerability and breathe out security of an IT system. And risk is defined as the probability of the exposure or loss resulting from a cyber attack. Some examples of threats, for example, in malware, phishing, passcode attack, distributed denial of service, and malvertising, and driven by download, and something like that, that may affect the performance of whole system, and can come from different sources, such as, for example, I don't know, data protection, mobile technologies, and multiple vendor and multiple technologies and global business that that necessitate to make the whole system more secure. There are different type of actors in the cyber attack. Sometimes governments, sometimes activism, internal users, and hackers. For example, hackers may be attackers that are paid by some person or public organization, but the government may have some financial or political issues for cyber attack. Sometimes these cyber attack will be done by activism that are similar to government, but do not have much financial power, almost. As a motivation factor, we should have some political actions, sometimes gaining money, and sometimes just playing a role in different aspects that the hacker decide to attack on a system. The threats on a data communication system will include some destruction, sometimes modification of information, not destruction, sometimes theft or removal or loss of information, sometimes disclosure of some information that shall not be disclosed, and sometimes interruption of services, of special services. Threats can be accidental. Accidental threat do not involve necessarily malicious intent. Sometimes intentional, that's require a human or with intent of a violent security. If intentional threat result to an action, it becomes an attack that sometimes will be passive or active. Passive threats do not involve necessarily any change to the system, and active ones involve sometimes significant changes to the system. I want to ask Dr. Sharifi that how many minutes will we have?
Dr. Baghai, thank you very much for your presentation, but I must say that your time is over, and we should have a part of Q&A, and maybe we have only 5 minutes for the Q&A part. So that your time is over, okay?
Okay, in the next slide, I provide some details and examples for attackers and their effect on the performance of, for example, SCADA system and the electricity market, the audiences, I think if we have more time, I can explain. If not, they can follow from the papers that we recently published in my Google Scholar and my website, of course. If please inform me if the time is over. Just 5 minutes later, I should continue. Yes?
Yes, please continue until 18:30, okay? I mean 6:30 p.m.
6:30. Okay. I mentioned that the attacks can be passive or active. In the active attack, the data is modified and false data is delivered to the receiver. But in the passive, intruder collects the data and not necessarily modified and delivered some false data to the receiver. We should experience denial of service as explained in the previous lectures. Denial of service in this situation, a hacker prevents authorized user from accessing to a system. And in DDoS, DDoS briefly, multiple source attack to server are done, and this is an attack on the availability of the whole system. That absolutely affect the performance of the whole system. To prevent denial of service, we should use firewall or implement on different parts of the system that work are almost based on internet protocol, as I mentioned in the slides that I was explaining about the Internet of Energy. And disadvantage of using this kind of firewalls is that in a smart grid we may have many devices that this solution will be made sometimes expensive or expensive to be used in different hardware protection for all of devices. In the next part, I review the cyber attacks in power system and power grids from beginning to end, and also I should mention that I have one invited lecture in one of the IEEE conferences in Croatia, in SGMA conference in Croatia, that in near future I will announce in my LinkedIn profile. The audiences shall follow some concepts in this tutorial. I will provide the link in my LinkedIn, because if I start this slides and explain about the effects of cyber attack in the power system, I should explain at least 20 minutes later, and I think well, the audiences, of course, unfortunately, I cannot present these slides. The audiences can follow follow my website and follow the announcement in my LinkedIn for next invited lecture in SGMA conference, IEEE SGMA conference in Croatia. And in this lecture, I will explain about these concepts about cyber attacks in power system and definition, necessities, and some other aspects of cyber resiliency that should be considered in any power system. Because we have not much more time. If the audiences have any question, I can explain. If not, we can finish. I don't know. Dr. Sharifi will decide.
Okay. Your time is finished, Dr. Bahai. Thank you very much for your presentation. In this part, we have 5 to 10 minutes of Q&A in Persian language. Okay? So I would share my camera. And, okay. Go on. مثل آقای دوستینیا پرسیدن که ارتباطات ایونت تریگر هم میتونن به پیدا کردن سایبر اتک در میکروگریدز ها کمک کنن؟
فکر میکنم بله. البته این در واقع الگوریتم‌های وجود دارن، همونطور که خب البته خودتون آقای دکتر شریفی هم شما هم آقای پروفسور طالبی استاد هستین و بهتر از بنده میدونید این میتونه توی یه در واقع کنترل آرکیتکچر به خوبی تعریف بشه و یه رزیلینت ایونت تریگر در واقع الگوریتم برای سیستم هایی که در واقع فیس هستن با تایپ های مختلفی مثل دیداس یا DOS یا دیسپشن اتک ها یا چیزهای دیگه در واقع تعریف بشه. ما یک نمونهش رو ضمن البته ببخشید من یادم رفت سلام مجدد فارسی به همه عزیزان، ما یه نمونهش رو توی یکی از پیپرهایی که مال یکی از دانشجوهامون توی دانشگاه امیرکبیر بود آقای افشاری توی ICRoM سیستم جورنال پابلیش کردیم که حالا من عرض کردم توی وبسایت رو در واقع گوگل اسکولار من هست و دوستانم میتونن بررسی کنن. البته کارهای دیگه بچه‌ها هم هست که توی 1-2 سال اخیر کار کردیم، ولی توی این نمونه فکر می‌کنم به اون پیپرها رجوع کنن در واقع جواب این سوال هست.
بله خیلی ممنونم. من خواهش می‌کنم آقای دکتر طالبی و آقای دکتر دیباجی هم به جمع ما بپیوندن. حالا اگه میتونن دوربین هاشون رو هم شیر بکنن یه چند دقیقه‌ای، اگر دوستان سوالی دارن از اسلایدهای قبلی، از پرزنتیشن های قبلی و پرزنتیشن های دکتر بقایی در خدمت دوستان باشیم. اگر هم که سوالی نیست که خب به هر حال اگر نکته پایانی هست توسط های دکتر دیباجی های دکتر طالبی خوشحال میشیم که بشنویم. البته من فکر کنم 3 نفر بیشتر نمیتونن دوربین بدن.
لذا محدودیت داریم.
بله اگر آقای دکتر طالبی خواستن دوربین بدن من دوربینم رو خاموش میکنم.
آره من
جان راحت باش، راحت شما به هر حال جوونا. من باز عذرخواهی میکنم که من آقای دکتر دیواجی و دکتر بقایی رو فراموش کرده بودم اسمشون رو بگم، خیلی زحمت کشیدن تو ارائه. از هر دوشون ممنونیم و نه شما بدین، شما خوش تیپات دوربین بدین به هر حال جذاب‌تره.
آقای دکتر طالبی ببخشید ما جسارت کردیم محضر شما، اونی که در واقع مراجعه کردیم درسایی بود که تو دوران شاگردی شما آموخته بودیم، فقط بخش ما در محضر شما
خیلی ممنون
به که ما بردن بود. ببخشید دیگه.
بله بسیار عالی. خب آقای سلطانی فکر کنم سوال دارن.
بله سلام، صدامون دارید؟ سلام.
بله بفرمایید.
سلام و عرض ادب خدمت اساتید گرامی. من خدمت دکتر دیواجی سوال داشتم مربوط به ارائهشون. توی شبکه‌ای که حالا ما نشون دادید مثلا 6 تا نود داریم، بعد یه نودی که شما اون وسط بود اگه اشتباه نکنم گره 6 بود، اطلاعاتی که میفرستاد مثلا اشتباه میفرستاد و اون یکی ها میفهمیدن که از گره های قبلی داده گرفتن این اشتباه فرستاده. سوال من اینه حالا اگه یکی از گره هایی که مثلا گره سوم داره داده به یه گره میفرسته و اون گره از طریق اون تشخیص میده که گره قبلی که داده بهش داده اشتباه فرستاده و مالیشیس بوده، شاید در اثر یه سری از رخدادهایی که تو شبکه اتفاق میفته اون گرهی که دادش رو میفرسته نتونه بفرسته. این گره چجوری داره تشخیص میده اون قبلیه که فرستاده مالیشیس بوده؟ یعنی یه ترشولدی هست یا چجوریه؟ نمیدونم حالا سوالم واضح بود یا نه.
منم مطمئن نیستم که درست متوجه شده باشم. اول سلام میکنم خدمتتون و همه حضار، خیلی از آقای دکتر شریفی، دکتر طالبی، دکتر بقایی و دو تا دانشجوی عزیز خانم فیروزمند و خانم بهنیا خیلی تشکر میکنم و حضار که خب وقتشون گذاشتن و صبوری کردن. خدمتتون عرض کنم که ببینید یه دلیلی داشت که حالا من تو پرزنت نکردم خیلی که تأخیر رو آوردم تأخیر دلیلش همینه که ما معمولا در عمل همون اتفاقی که شما میگید میفته، هرچند خیلی کوچیک، ولی یکی از اشتباهاتی که به نظر من ما توی تئوری کنترل میکنیم اینه که همه چی فرض میکنیم اینستنتلی داره انتقال پیدا میکنه. اینجا اون تأخیر اگر که خیلی طولانی بشه، یعنی عملا میشه denial of service. خب حالا نه به صورت اتک، یا میتونه مثلا on available باشه. در اون صورت همون، حالا نمیدونم شما بودین این سوالو پرسیدین یا نه،
بله بودم،
تحت تاثیر قرار نمیگیره. به این دلیل اگر که به این شرط که اونی که نمیاد رو شما جزء بیزانتینا در نظر بگیرید. توجه کردید؟
بله. یعنی
اون نوت، چون که اونایی که سالمن فرض میشه که آن تایم تو اون زمانی که باید این اصطلاح، من جامعه تغییر بدم این نور پشت سرم خیلی داره اذیت میکنه، آن تایم دارن اطلاعات منتقل میکنن. اگه یه چیزی نمیاد آن تایم و اصلا نمیاد، یعنی با یه دیلی قابل قبولی که باندش هم میدونی نمیاد، اونو فرض کنید جزء بیزانتیناست.
خب
اگر
من میتونم یه سوال بپرسم آقای دکتر؟ خب ما الان یه دونه گره ملیشز داریم، خب بدکار داریم، بعد الان داره 50-50 انجام میده کاراشو. بعضی وقتا اطلاعات اصلا درست میفرسته، بعضی وقتا اشتباه میفرسته. ما چه ترشولدی داریم تو شبکه که تشخیص بدیم ملیشز یا نه؟
ببینید اینا همه، ببینید تعریف مالیشس اینه که رفتاری که شما ازش انتظار دارید انجام نمیده. این یکی از هموناست. شما میتونید همون مثالی که زدم که مثلا نود فکر میکنم 4 بود که مثلا اومده بود پایین، بعد یه جای ثابت مونده بود، شما میتونید بیاد روی 4 وایسه، بعد بیاد پایین، بعد دوباره بره بالا، بعد مثلا آن اویلیبل بشه. اینا همه میتونه توی تعریف بگنجه. اینا همه میتونه مالیشس باشه و الگوریتم کار میکنه. مشکلی با الگوریتم ایجاد نمیشه. متوجه هستید چی میگم؟ ممکنه اگر شما این اضافه کنید مجبور بشید یک چیزی اضافه بکنید توی الگوریتم، ولی نه یه چیز خیلی عجیب غریبی. مثلا ممکنه بگید که اگه نیامد تا این باند، یعنی بیشتر از دیلی بود، فرض کنید اون مقدار مثلا بی‌نهایت، اون مقداری که خب مشخص میشه. متوجه چی میگم؟
پس باید یه ترشولد این وسط داشته باشیم در این باره.
ببینید ترشولد که آخه عرض کردم خدمتتون، دیلی اگه داشته باشید، اون دیلی همون ترشولده. توجه کردید؟ اون دیلی که شما میذارید ترشولده و ترشولد روی ولیو نمیتونید بذارید. اگه سوالتون اینه روی ولیو اگر بذارید مشکلش ابهامی که ایجاد میشه. اون ترشولد میخواید چی مقداری بذارید؟ میخواید 100 بذارید، 500 بذارید، 2 میلیون
مثلا بگیم 5% از پکیتایی که میاد اگه دراپ شد مشکل نداره، یا 10% اگه بیشتر از اون بود.
میگید چرا نمیگید 50%؟
خب میگم 1%. حالا نمیدونم، من سوال بود این پرسیدم.
ببینید اگر که شما مشکل نداره، شما هر چیزی میتونید اضافه کنید، ولی الگوریتم به طور فاندامنتال، به طور بنیادی تغییری نمیکنه. همونجور که گفتم، یعنی شما میتونید این فرض رو بذارید که یه سری هم نمیفرستن به صورت فالتی. وقتی یه مسئله دیگه یه دارید حل میکنید، ولی خیلی راه حل متفاوتی لازم نیست ارائه بدید. متوجه چی میگم؟
بله، بسیار ممنونم. دستتون در نکنه. ممنون از ارائهتون. تشکر.
سلامت باشین. ممنون شرکت کردید.
خیلی ممنون. یه سوال آقای یا خانم اصغرپور پرسیدن که ماکسیموم تأخیر قابل قبول.
ببینید تأخیر میتونه ماکسیمومش خیلی زیاد باشه، منتها اون کی باری که در واقع ما میتونیم همه رو ریتریو بکنیم، همه اینیشال ولیو رو داشته باشیم که بعد مثلا به اوریج کانسنسس برسیم، اون زیاد میشه. الان من البته اسلایدها رو نمیخوام شیر بکنم، ولی برای اینکه خودم یادم یا دقیقاً ولیویی که داشتیم چقدره. ببینید ما اینجا گفتیم که واسه اسینکرونس کی بار باید بزرگتر یا مساوی n-2 ضرب داره کی بار پلاس تا بار باشه. شما این تا بار اون آپر بانده. این تا بارا اگه اوکی هستید با یک کی بار مثلا خیلی بزرگ، تا بارا میتونید همون قد برید بالا، مشکلی نداره.
بله خیلی ممنون. آقای مهرانفر سوال دارن. آقای مهرانفر شما سوال دارید؟ اگر دارید حرف میزنید احیانا ما صداتون رو نداریم. آقای مهرانفر اگر احیانا حرف میزنید ما صداتون رو نداریم، بنابراین توی چت باکس لطفاً تایپ کنید. بقیه دوستان اگر سوالی دارن
ببخشید دکتر صدا
الان میاد، الان میاد، بفرمایید.
من این سوال داشتم، حالا شاید از دکتر بقایی بیشتر مربوط بشه. ما تو حالا هر صنعتی یک سری استانداردها رو برای سنسورها و میزان خطاشون تعریف میکنیم.
خب صداتون دوباره قطع شد آقای، اصلا فکر کنم رفت بیرون از اتاقشون، فکر کنم اینترنتشون قطع شد.
الان دکتر صدا هست؟
الان میاد، بله.
من خواستم بگم یه سری استانداردهای ما توی اندازه‌گیری‌ها داریم که فرضاً مثلا تو حوزه نفت برای بحث‌های فالت و اون اختلاف هم مقدار واقعی یک سری فاصله‌هایی رو تعریف می‌کنن که در این فاصله اندازه‌گیری‌ها استاندارد هست. خواستم ببینم در خصوص بحث‌های حملات سایبری آیا توی استانداردهایی که در جهان هست تعریف هایی برای این مسائل، یعنی اتفاق افتادن یک حمله و بحث اندازه‌گیری‌هاش که حالا ممکنه مثلا توی بحث‌های فروش یا الوکیشن مثلا نیاز باشه، آیا استانداردهایی وجود داره یا مثلا معیارهای تعریف شده که در این مواقع مثلا باید چجوری عمل کرد؟
بله. ارزم خدمتتون که توی IEC 850
آقای مهران میکروفونتون رو خاموش کنید.
مرسی. و توی IEC 61850 و IEEE 800 و 801ش در واقع دو تا جدول داره که در واقع به این پرداخته. اما بر اساس چیزی که چون شما فرمودید که توی بازار آیا این ریویو شده یا نه، IEEE توی پاور انجینیرینگ سوسایتیش دو تا تاسک فورس داره، یکیش مال در واقع همین سایبر رزیلینسیه و یکی دیگه هم مال در واقع بیگ دیتا است که در واقع در آینده نزدیک احتمالاً داره در واقع ادغام میشه. اون یکی از کارهایی که قراره تو این در واقع تاسک فورس انجام بدیم و منم حالا از 2021 خوشبختانه بهش اضافه شدم، پیاده سازی و در واقع درآوردن این الزامات برای اینکه پیشنهاد بدیم که آیا مثلا استاندارد 61850 باید در واقع الزامی بهش اضافه بشه توی ادیشن‌های جدیدش یا نه. این در واقع چیزی که توی این تاسک فورس قراره در واقع بررسی بشه و انشالله ارائه بشه.
بله، خیلی ممنونم.
بسیار
ممنون. دوستان بازم سوالی هست؟ بله. پرسیدیم اینو آقای لاری؟ من این خودم به فارسی از آقای دکتر دیباجی پرسیدم. نه از شاید هم از آقای دکتر دیباجی پرسیدم.
دکتر بقایی پرسید.
شاید از دکتر بقایی پرسیدم.
آره بله من عرض کردم، توضیح دادیم فکر می‌کنم.
بله خیلی ممنونم آقای مهندس لاری. خب ما چون یه ذیقه وقتی داریم 6:45 دیگه باید تمامش بکنیم، من خواهش میکنم اگر سخن پایانی هست آقای دکتر طالبی در خدمتتون باشیم، بعد بقیه دوستان هم به ترتیب میایم خدمتشون. آقای دکتر طالبی سخن پایانی دارید شما؟
من تشکر میکنم از همه دوستانی که شرکت کردن. تشکر ویژه هم دارم از آقای دکتر دیباجی در باستان، آقای دکتر بقایی، جناب عالی و خانم ها فیروزمند و بهنیان. انشالله که ورکشاپ به درد بچه ها خورده باشه و مطالبی رو فرا گرفته باشم. خیلی
ممنون از شما. آقای دکتر دیباجی در خدمتتون هستیم.
منم خب خیلی خوشحالم راستش که همچین ورکشاپی داره برگزار میشه. خیلی 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 کار خوبی کردین که این ورکشاپ برگزار کردین. و یه چیزی رو خواستم به صحبت آقای بقایی اضافه بکنم که یکی از نکاتی که اتفاقا خیلی جالبه این سوال، یکی از نکاتی که باید در نظر داشت اینه که اون اتکره حالا از زوایای مختلف میشه اینا اینداستریال اپلاید نگاش کرد، ولی اون اتکر سعی میکنه در قالب استانداردها جوری که پذیرفته شده است کارش انجام بده. یعنی اون دیناین آف سرویس یا فالس دیتا اینجکشن یک جوری باشه که شما را تشخیصش ندید که سیستم پروتکشن حالا تو مایکروگرید و اینها که پاور سیستم خیلی اینستا داریم اینها جلوشو نگیره. لذا این نکته خیلی جالبیه. حالا از این زاویه همیشه بهش نگاه کرد. اما نکته خاصی من ندارم حقیقتش. انشالله که موفق باشید و سوالی هم بود احساس نکنید غریبه اید، راحت بپرسید.
بله خیلی ممنونم. آقای دکتر بقایی در خدمتتون هستیم.
خیلی ممنون آقای دکتر شریفی، دستتون درد نکنه. هم از شما تشکر میکنم، هم از آقای دکتر طالبی که به هر حال شاگردای قدیمیشون رو یه بار دیگه دوره هم جمع کردن تو این ورکشاپ. حالا چه از مخاطبین چه از ماهایی که در واقع درسایی که آموختیم پس دادیم، خیلی هم خوشحال شدم. حالا شما رو با آقای دکتر که زیارت میکنیم، ولی بعد از چندین سال آقای دکتر دیواجی رو بعد از سالهایی که تو دانشکده بودن خلاصه زیارت کردیم و انشالله که همگی موفق باشید. ممنون از همگی.
خیلی ممنون از شما. منم تشکر میکنم از همه حضار محترم، از پرزنترهای محترم، جناب آقای دکتر طالبی، آقای دکتر دیواجی، آقای دکتر بقایی، خانم مهندس فیروزمن و خانم مهندس بهنیا، به خاطر ارائه های خیلی خوبی که انجام شد و من حقیقتا خودم خیلی چیز یاد گرفتم. ممنون هستم از همگی. ما انشالله قراره که ادامه بدیم این ورکشاپ ها رو، اگر زنده باشیم و پرزنترهای محترم قابل بدونن این ورکشاپ ها ادامه پیدا کنه برای حالا کنفرانس های دیگه ای که داریم. اگر دستاوردهای جدیدتری داشتیم بتونیم خدمت شما دوستان ارائه بکنیم و خیلی خوشحال میشیم که توی تیم تحقیقاتی که داریم اون دوستانی که واقعا علاقه‌مندن که کمک بکنن یا در واقع فکر میکنن که ما میتونیم کمکی بهشون بکنیم به این تیم تحقیقاتی بپیوندن. حالا از مادریتورهای روم میتونید آدرس های ما رو دریافت بکنید یا همون QR کدی که اول جلسه ارائه دادم اطلاعات افراد هست، میتونید ایمیل بزنید و انشالله در ادامه کار بتونیم تیممون رو یه مقداری بزرگتر هم بکنیم تا کارهای بزرگتری رو انجام بدیم. خیلی ممنون از همه دوستان. از خانم فیروزمند و بهنیا هم تشکر میکنم. اگر این دوستان هم حرفی دارن در خدمتشون هستیم، اگر نه که دیگه جلسه رو به پایان ببریم. خانم فیروزمند و بهنیا.
نه استاد خیلی ممنون از اساتید محترم و ارائه‌شون و همچنین دوستانی که این ارائه شرکت کردن.
خواهش میکنم. سلامت باشید. خانم بهنیا شما چطور؟
نه خیلی بر من یک تجربه خیلی خوبی بود که در کنار اساتید با تجربه و فرهیخته مثل شما دکتر دیواجی، دکتر طالبی و دکتر بقایی بتونم که این تجربه رو حاصل کنم. مرسی، خیلی ممنونم.
ممنون از همگی. به امید دیدار در ورکشاپ های بعدی و مراحل بعدی. خدا نگهدار همگی.
خدا.
ممنون از همگی. خدا نگهدار.
خدا حافظ.
خدا.